You think you know where you are right now. You're on Earth. Earth orbits the Sun. The Sun sits in the Milky Way galaxy. And the Milky Way? It's just one of billions of galaxies scattered across the cosmos. Simple, right? Wrong. Because there's something we haven't told you. Something that changes everything about our cosmic address. We're not just floating through space. We're floating through nothing. A void. An immense, almost empty bubble in the universe that stretches across 1 billion light years. And here's the problem. It shouldn't exist. Or rather, we shouldn't be inside it. Because being here in this cosmic desert is making us see the universe differently than everyone else would. And that difference, it might mean everything we think we know about the fate of the cosmos is wrong. Let me take you back to a moment in 2013. A team of astronomers led by Amy Barger, Ryan Keenan, and Lennox Cowie were doing what astronomers do: mapping galaxies. Not just a few galaxies, thousands of them. They were measuring distances, plotting positions, building a three-dimensional map of our cosmic neighborhood. And that's when they saw it. Pattern, or rather, the absence of a pattern. Imagine you're looking at a city from above at night. You see clusters of lights, streets connecting them, neighborhoods blending into one another. Now imagine flying over a region and seeing nothing. No lights, no streets, just darkness. That's what these astronomers found. An enormous region of space centered roughly on us where galaxies simply weren't. They called it the KBC Void, named after their initials. And here's the staggering part. This void is about 1 billion light years across. To put that in perspective, if you could somehow travel at the speed of light, it would take you 1 billion years just to cross from one side to the other. That's not a neighborhood. That's not even a city. That's like discovering your house is built in the middle of an ocean and the nearest land is 1,000 miles away in every direction. Now, you might be thinking, so what? Space is big, really big. Why does it matter if we're in an empty region? Because voids like this aren't supposed to exist. Not on this scale. Not with us inside them. The universe, when you zoom out far enough, looks like a cosmic web. Galaxies cluster together in groups. Those groups form superclusters, and those superclusters line up along vast filaments of matter, like beads on a string. Between these filaments, voids, empty regions where matter was pulled away by gravity toward the denser areas. Think of it like soap bubbles. The soap molecules cluster along the thin walls and edges where bubbles meet, leaving the interior of each bubble mostly empty. The universe works the same way, just on an unimaginably larger scale. These voids are everywhere. They're a natural consequence of how gravity shapes the cosmos. But here's the thing, we shouldn't be inside one. Galaxies like ours, large spiral galaxies with active star formation, typically exist along the walls of voids or in the filaments between them. Finding the Milky Way deep inside a supervoid is like finding a thriving coral reef in the middle of a desert. It's not impossible. It's just unexpected. And that unexpectedness creates a problem, a big one, because being inside this void might be distorting our view of the universe itself. To understand why, we need to talk about the Hubble constant. This number, named after Edwin Hubble, who discovered the expansion of the universe in 1929, tells us how fast the universe is expanding. It's one of the most important numbers in all of cosmology. If you want to know how old the universe is, you need the Hubble constant. If you want to know what will happen to the universe in the distant future, you need the Hubble constant. If you want to understand dark energy, the mysterious force accelerating the expansion of space, you need the Hubble constant. It's not just a number. It's the key to understanding cosmic history and cosmic destiny. And here's the problem. We can't agree on what it is. There are two main ways to measure the Hubble constant. The first method uses the cosmic microwave background, the afterglow of the Big Bang itself. This light has been traveling through space for 13.8 billion years, and it carries within it a snapshot of what the universe looked like when it was just 380,000 years old. By studying the patterns in this light, the tiny fluctuations in temperature and density, we can calculate how fast the universe should be expanding today. The European Space Agency's Planck satellite did exactly this, producing exquisitely detailed maps of the cosmic microwave background. Their result? The Hubble constant should be about 67.4 kilometers per second per megaparsec. That means for every 3.26 million light-years of distance, space is expanding at 67.4 kilometers per second. It's a precise measurement, one of the most precise in all of astronomy. The second method is more direct. We look at objects in the universe whose brightness we can calculate. Supernovae, pulsating stars called Cepheid variables, red giant stars. These objects are like cosmic lighthouses. We know how bright they should be intrinsically, so by measuring how bright they appear from Earth, we can calculate their distance. Then we measure how fast they're moving away from us using the Doppler effect, the same principle that makes an ambulance siren change pitch as it passes you. By combining distance and velocity for hundreds of these objects at various distances, we can directly measure the expansion rate. Adam Rees of Johns Hopkins University, who won the Nobel Prize for discovering that the universe's expansion is accelerating, has been leading this effort. His result? The Hubble constant is about 73.5 kilometers per second per megaparsec. That's a difference of about 9%. In everyday life, 9% doesn't sound like much. But in cosmology, it's catastrophic. These are two independent, highly precise measurements that should give the same answer. They don't. And the more accurately we measure, the more certain we become that this discrepancy is real. We call it the Hubble tension, which sounds benign like a mild headache. But it's more like a fracture running through the foundation of modern cosmology. So what does this have to do with the void? Everything. Because if we're sitting inside an enormous underdense region of space, our local measurements of the expansion rate might be skewed. Think about it this way. Imagine you're measuring the flow rate of a river, but you're taking your measurements in a section where there's a large pool, a place where the water spreads out and slows down before continuing downstream. Your measurement would show a slower flow than someone measuring in the main channel. The KBC void might be doing something similar to our measurements of cosmic expansion. Matter inside a void feels less gravitational pull than matter in denser regions. Less gravity means matter can move more freely, which could make the local expansion rate appear faster than it actually is on cosmic scales. It's like we're sitting in a bubble within the universe, and from inside this bubble, everything looks slightly different than it would from outside. But wait, you might say, if we're in a void, why didn't we notice it sooner? How did we miss a billion light-year bubble of nothing with us at the center? The answer is frustratingly simple. It's hard to see emptiness. Galaxies are bright. They emit light across the electromagnetic spectrum. Voids, by definition, have very few galaxies, which means very little light. Mapping a void is like mapping a dark room. You can only see it by noting where things aren't. It requires surveying huge volumes of space, measuring distances to thousands upon thousands of galaxies, and then looking for patterns in the distribution. That kind of survey only became possible in the last few decades with automated telescopes and sophisticated computer analysis. The Sloan Digital Sky Survey, which began in 2000, was one of the first to create truly three-dimensional maps of the universe on large scales. And that's when voids started revealing themselves in their full, empty glory. The KBC void isn't alone, by the way. It's part of an even larger structure called the local hole or the local void, depending on who you ask and which scale you're considering. These nested structures of emptiness extend outward from our position, creating what some astronomers describe as a cosmic Swiss cheese, with us sitting in one of the larger holes. But the KBC void is special because of its size and because of how centered we appear to be within it. Some estimates put us within about 150 million light-years of the void's center. That's remarkably close to the middle, cosmically speaking. And that centrality raises questions. Are we actually near the center, or does it just appear that way because of observational biases? After all, we can only map what we can see, and we can only see so far before distance and darkness conspire to hide galaxies from our instruments. It's entirely possible that what we call the KBC void is actually part of an even larger underdense region that extends beyond our ability to map it. Let's zoom out for a moment and talk about what voids actually are. When the universe began 13.8 billion years ago in the Big Bang, matter wasn't distributed perfectly evenly. There were tiny fluctuations, regions that were slightly denser and regions that were slightly less dense. These differences were minuscule, less than 1 part in 100,000. But gravity doesn't care about how small a difference is. It only cares that a difference exists. Dense regions began attracting more matter, becoming denser still. Less dense regions lost matter to their denser neighbors, becoming emptier. Over billions of years, these tiny seeds of structure grew into the cosmic web we see today. The densest regions became galaxy clusters, collections of hundreds or thousands of galaxies bound together by gravity. The clusters connected along filaments, streams of galaxies flowing through space like tributaries feeding into rivers. And between these structures, voids, not completely empty, but significantly underdense, containing perhaps 1/10 the number of galaxies you'd expect in an average region of space. Most voids are between 30 and 300 million light-years across. They're cosmic bubbles in the foam of space. A few are larger. The giant void in the constellation Canes Venatici is about 1.5 billion light-years across, one of the largest known structures in the universe. The Boötes void, discovered in 1981, was one of the first supervoids ever found, and astronomers were so startled by its emptiness that they nicknamed it the Great Nothing. Inside these voids, galaxies are rare and often strange. They tend to be smaller, bluer, and younger than galaxies found in denser environments. That makes sense. In a void, there's less matter available to build large galaxies, and there are fewer interactions with neighbors to trigger star formation or galactic mergers. Void galaxies are loners, cosmic hermits living in the most isolated neighborhoods in the universe. Yet they're not completely isolated. Careful studies have shown that even within voids, galaxies align along tendrils of dark matter, invisible scaffolding that traces out the gravitational structure of space. These tendrils are like the thinnest threads in the cosmic web, barely there but still present, still guiding the motion of matter through the void. Dark matter. We need to talk about dark matter. Because voids aren't just empty of normal matter, the protons and neutrons and electrons that make up stars and planets and us. They're also relatively empty of dark matter, the mysterious substance that makes up 85% of all matter in the universe. Dark matter doesn't emit light. It doesn't absorb light. It doesn't interact with electromagnetic radiation at all, as far as we can tell. The only way we know it exists is through its gravitational effects. Galaxies rotate too fast to be held together by the gravity of their visible matter alone. There must be additional mass we can't see. Galaxy clusters contain galaxies moving so quickly they should fly apart. Dark matter provides the extra gravity to keep them bound. The cosmic microwave background shows patterns that only make sense if dark matter was present in the early universe, creating gravitational wells that normal matter fell into. Every line of evidence points to the same conclusion. Most of the matter in the universe is invisible. And in voids, there's less of it. Not none, but less. Which means the gravitational landscape inside a void is flatter, smoother, with gentler hills and valleys than the dramatic peaks and canyons found in denser regions. This matters because gravity doesn't just hold things together. It also affects the expansion of space itself. General relativity, Einstein's theory of gravity, tells us that matter and energy curve spacetime. The more matter in a region, the more curved spacetime becomes, and the more gravity affects the motion of objects. But expansion works differently in curved versus flat spacetime. In a dense region, packed with matter and dark matter, gravity works to slow the expansion. Matter pulls on matter, trying to reverse the expansion and collapse everything back together. In an underdense region like a void, there's less matter pulling back, which means expansion proceeds more freely. This creates what physicists call a differential expansion rate. Space expands faster in voids than in dense regions. Not by much, but measurably. And if you're measuring the expansion rate from inside a void, you might naturally conclude that the universe is expanding faster than it actually is on average. It's like trying to judge the temperature of an entire building while standing next to a heater. Your local measurement is accurate for where you are, but it's not representative of the whole. This brings us back to the Hubble tension. Could the KBC void explain why local measurements of the expansion rate are higher than predictions from the cosmic microwave background? Some researchers think so. If we're in a region where space expands slightly faster than average, our direct measurements using supernovae and other distance indicators would naturally yield a higher value for the Hubble constant. The cosmic microwave background, on the other hand, gives us an average over the entire observable universe. It doesn't care whether we're in a void or a cluster. It's measuring the global expansion rate, not our local one. So the tension might not be a sign that our physics is wrong. It might just be a sign that our location is atypical. We're measuring the universe from an unusual vantage point, and that's giving us an unusual result. But here's where it gets complicated, because other researchers strongly disagree with this explanation. They've run simulations modeling how voids affect expansion measurements, and they argue that even a void as large as the KBC void isn't enough to explain the full magnitude of the Hubble tension. The void might account for 1 or 2 kilometers per second per megaparsec of the discrepancy, but not all 6. To fully explain the difference, we'd need to be in an even larger, even more underdense void, something so extreme that we should have noticed it long ago. Plus, there's another problem. If the void explanation is correct, then we should see the expansion rate gradually change as we look at objects at different distances. Objects closer to us, deep within the void, should show a higher expansion rate. Objects farther away, outside the void, should show a lower rate. We should see a transition, a boundary effect. Some studies claim to see hints of this, a gradual decline in the measured Hubble constant as we look further out. But other studies don't see it, or they see conflicting patterns that don't match the void prediction. The data is messy, as data often is in astronomy, and different analysis methods produce different conclusions. So we're left in a frustrating position. We know we're in a void. We know there's a discrepancy in the expansion rate. We strongly suspect these two facts are connected, but we can't prove it. Not yet. Not with the data we currently have. What we need are better measurements, more precise distance indicators, surveys that push deeper into space to map the true extent of the void and see where it ends. We need to measure the expansion rate at multiple distance scales and look for the smoking gun, the clear signature that would tell us, yes, the void is responsible. Or no, something else is going on. Because if the void isn't responsible, then the alternatives are even more intriguing. Maybe the physics we use to interpret the cosmic microwave background is wrong. Maybe dark energy, the force driving the accelerated expansion, is more complicated than we thought. Maybe the universe's expansion isn't even uniform, and different regions are expanding at fundamentally different rates for reasons we don't yet understand. Any of these possibilities would revolutionize cosmology. They would force us to rewrite textbooks, reformulate theories, and rethink everything we believe about the universe's past and future. Let's talk about what it means to live in a void. Not physically, obviously. The void doesn't affect Earth in any tangible way. You can't feel it. It doesn't change the weather or tug on the oceans. On human scales, even on galactic scales, the void is irrelevant. Gravity holds the Milky Way together just fine, regardless of how empty the region around us is. Our local group of galaxies, which includes the Milky Way, Andromeda, and about 80 smaller galaxies, is gravitationally bound. We're not expanding apart. In about 4 billion years, the Milky Way and Andromeda will collide and merge, creating a giant elliptical galaxy that astronomers have already nicknamed Milkomeda. The void won't stop that, but the void does affect our view. It affects what we see when we look out into the universe. Galaxies and voids are farther apart, which means there's more space between them, which means more opportunities for light to be stretched by the expansion of space as it travels toward us. This redshift, the lengthening of light waves into redder colors, is one of our primary tools for measuring distances in cosmology. But if we're in a void, the relationship between redshift and distance might be slightly different than we assume. Not hugely different, but different enough to introduce systematic errors into our measurements. There's also a philosophical dimension to being in a void. It highlights how contingent our knowledge is, how dependent on our position. Throughout history, humans have had to grapple with the realization that we're not at the center of things. Copernicus showed that Earth isn't the center of the solar system. Shapley showed that the Sun isn't at the center of the Milky Way. Hubble showed that the Milky Way isn't at the center of the universe. In fact, the universe doesn't have a center. Every point in space sees roughly the same large-scale structure, the same cosmic web of filaments and voids, the same expansion in all directions. This is the cosmological principle. The idea that the universe is homogeneous and isotropic on large scales, that every observer sees essentially the same universe. But the void challenges this just a little, because if we're in an underdense region, our local universe isn't quite average. It's statistically atypical, not radically so, but enough to matter. And that raises the question, how many other assumptions have we made based on our particular location? What else are we seeing through a slightly distorted lens? Some scientists have pushed this idea even further. They've proposed that maybe, just maybe, we're not in a void at all. Maybe the opposite is true. Maybe we're actually in an unusually dense region, and what we interpret as a void is actually the normal density of the universe, with everything else being overdense. This sounds absurd at first, but bear with me. The cosmic microwave background tells us the average density of matter in the universe. About 5 protons per cubic meter on average across all of space. But that's an average. Some regions are denser, some are less dense. What if our measurements of the local universe, the matter we can actually see and count in our cosmic neighborhood, have been systematically underestimating the density? What if there's more dark matter here than we think, making this region denser rather than less dense? If that were true, it would flip the entire void interpretation on its head. But most astronomers don't buy this alternative. The evidence for underdensity is strong. Galaxy counts, matter distributions, gravitational lensing studies. Multiple independent lines of evidence all point to the same conclusion. We're in a region with less stuff than average. A void by any reasonable definition. Now let's consider the formation of the KBC void. Voids don't appear suddenly. They grow over billions of years as matter drains out of underdense regions and flows toward overdense ones. Computer simulations of cosmic structure formation show this process in beautiful detail. Start with a nearly uniform distribution of dark matter in the early universe, add slight variations in density, then let gravity do its work. Fast forward through billions of years, and you see the cosmic web emerge. Filaments, clusters, and voids. The voids expand as matter leaves them. They're not static. They're dynamic, growing structures. The largest voids, like the KBC void, would have started as slight underdensities in the primordial universe, perhaps just a few % less dense than average. Over time, as structure formed around them, matter flowed out along the paths of least resistance, following the pull of gravity toward forming galaxy clusters and filaments. The void expanded, its boundaries pushed outward by the exodus of matter. Today, billions of years later, we see the result. A vast, relatively empty bubble in the cosmic web. But here's an interesting twist. The Milky Way wasn't always inside this void. Galaxies move. They orbit within clusters, they fall along filaments, and yes, they can cross from one environment to another. The Milky Way and our local group are actually moving through space at about 630 kilometers per second relative to the cosmic microwave background. That's over 2 million kilometers per hour. We're not stationary. We're on a journey through the cosmos, and that journey has taken us through different environments over the eons. Some researchers suggest that the Milky Way might have formed outside the void, in a denser environment, and drifted into it over time. Or perhaps the void expanded around us as we moved, and we just happened to be in the wrong place at the wrong time. The details are murky because tracking galactic motions over billions of years is extraordinarily difficult. We can measure where things are now and how fast they're moving, but reconstructing their full orbital histories requires modeling the gravitational influences of all nearby structures, both visible and dark. It's like trying to figure out where a ship came from by looking at its current position and heading, without knowing what currents and winds affected it along the way. There's another complication. The void might not be as empty as we think. Recent studies have started finding more structure inside voids than expected. Small galaxies, dim galaxies, galaxies that are hard to detect because they're not very bright or they're at inconvenient distances. Every time we build a more sensitive telescope, we find more galaxies in places we thought were empty. The Hubble Space Telescope revolutionized our understanding of void galaxies by detecting faint, distant objects that ground-based telescopes missed. The James Webb Space Telescope, launched in 2021, is continuing this work, peering even deeper and revealing the faintest galaxies ever seen. Some of these galaxies are in voids, challenging our understanding of how empty these regions truly are. It's possible that voids contain more matter than we've accounted for, not in big, bright galaxies, but in smaller, dimmer ones that add up to a significant population. If so, the KBC void might be less underdense than we think, which would weaken its ability to explain the Hubble tension. Or it might mean that voids have a more complex internal structure than simple models predict, with variations in density that create substructure within the larger emptiness. Dark energy. We need to circle back to dark energy, because if voids can affect our measurements of the Hubble constant, they might also affect our understanding of dark energy. Dark energy is the name we give to whatever is causing the universe's expansion to accelerate. Discovered in 1998 through observations of distant supernovae, dark energy appears to be a property of space itself. The more space you have, the more dark energy you have, and the stronger the push to make space expand faster. It's deeply weird. Most forms of energy dilute as the universe expands. Spread the same amount of energy over more volume, and you get lower density. But dark energy doesn't dilute. Its density remains constant even as space expands, which means the total amount of dark energy increases over time. It's as if every cubic meter of empty space comes with a fixed quantity of energy built in, and when you create more cubic meters through expansion, you create more energy. This violates our intuitions about conservation of energy, but general relativity allows it. In Einstein's equations, dark energy appears as the cosmological constant, a term Einstein himself added and then later called his greatest blunder, before it turned out to be real after all. Or at least something that acts like a cosmological constant. Here's the thing, though. We don't actually know what dark energy is. The cosmological constant is the simplest explanation, but there are alternatives. Maybe dark energy isn't constant. Maybe its strength changes over time or varies from place to place. Maybe it's not a property of space at all, but a sign that our theory of gravity needs modification on cosmic scales. These alternatives go by names like quintessence, modified gravity, or FR theories, and they all make slightly different predictions about how the universe expands. If we're in a void, and if our measurements of the expansion rate are skewed by that void, then our estimates of dark energy strength are also skewed. We might be overestimating how much dark energy there is, or underestimating it, depending on how the void affects the measurements. This matters because dark energy determines the universe's fate. If dark energy is weak, the expansion will continue forever, but slowly, and the universe will gradually grow cold and dark as stars burn out. If dark energy is strong and getting stronger, a scenario called the Big Rip becomes possible, where the expansion accelerates so much that it eventually tears apart galaxies, stars, planets, and even atoms. Our measurements right now suggest we're headed for a slow, cold death, not a cataclysmic rip. But if the void is affecting those measurements, we might be wrong. consider also what voids tell us about the distribution of dark matter. Dark matter is invisible, but its gravitational effects are not. We can map dark matter by looking at how it bends light, a phenomenon called gravitational lensing. When light from a distant galaxy passes near a massive object, the object's gravity bends the light's path, distorting the galaxy's appearance. By studying these distortions, we can infer where the dark matter is and how much there is. Gravitational lensing studies of voids show that they do contain dark matter, just less of it than average regions. The dark matter in voids is distributed in a sparse network of filaments, a faint echo of the cosmic web's larger structure. These filaments are where you find the few galaxies that do exist inside voids. They're like oases in a desert, places where just enough matter collected to allow stars and galaxies to form. But the filaments are thin and widely separated. Most of the void's volume contains almost no dark matter at all. It's as close to true emptiness as the universe gets. This brings up a profound question about the nature of space itself. Is empty space actually empty, or does it contain something we haven't detected yet? Quantum field theory, the framework that describes the fundamental forces and particles of nature, says that empty space isn't empty. It's filled with quantum fields, and these fields constantly fluctuate, creating virtual particles that pop into existence and annihilate in fractions of a second. These vacuum fluctuations have real, measurable effects. They're responsible for phenomena like the Casimir effect, where two metal plates placed very close together in a vacuum experience an attractive force due to the difference in quantum fluctuations between them and outside them. Could these fluctuations have something to do with dark energy? Many physicists think so. The problem is that when you try to calculate the energy density of vacuum fluctuations using quantum field theory, you get an answer that's about 10 to the power of 120 times larger than the observed dark energy density. That's a 1 followed by 120 zeros. It's not just wrong. It's spectacularly wrong, the worst prediction in the history of physics. Something is clearly missing in our understanding, either about quantum field theory or about gravity or about how they interact. Voids, as regions of especially empty space, might be laboratories for studying these questions. If vacuum energy varies from place to place, voids would be where the effects are most noticeable. Let's talk about observational challenges. Mapping voids is hard, really hard. Galaxies are point sources of light. You can take a picture and see where they are. Voids are the absence of those point sources. You can only map a void by measuring the positions of everything around it and noting where the galaxies stop. This requires large surveys, covering huge swaths of the sky, measuring distances to millions of galaxies. The Sloan Digital Sky Survey did this for the northern sky. The 2-degree field galaxy redshift survey did it for the southern sky. More recent surveys like the Dark Energy Survey and the upcoming Vera-C Rubin Observatory's Legacy Survey of Space and Time will provide even more data, mapping billions of galaxies and revealing void structures in unprecedented detail. But even with all this data, there are limitations. We can only measure distances to galaxies bright enough to detect. Dim galaxies, small galaxies, galaxies obscured by dust or hidden behind brighter objects. These might be present in voids but missed in our surveys. It's like trying to map a city at night by looking at streetlights. You'll see the major roads and intersections, but you'll miss the alleyways and residential streets that don't have lights. Distance measurements in cosmology rely heavily on redshift, the stretching of light due to the expansion of the universe. The more a galaxy's light is redshifted, the farther away it is, and the longer ago its light was emitted. This works beautifully for distant galaxies, where the expansion of space is the dominant effect. But for nearby galaxies, especially those within a few hundred million light-years, things get complicated. Galaxies aren't just moving away from us due to expansion. They also have their own peculiar motions, individual velocities caused by gravitational interactions with neighbors. These peculiar motions can add to or subtract from the expansion velocity, creating scatter in the relationship between redshift and distance. In a void, Where galaxies are sparse and gravitational interactions are weak, peculiar motions are smaller than in dense regions. But they're not zero, and they introduce uncertainty into our distance measurements. To truly map the void structure, we need distance indicators that don't rely on redshift, things like Cepheid variables, red giants, or supernovae. But these objects are rare and difficult to observe at the distances we're talking about. It's a game of trade-offs. Use redshift and survey millions of galaxies quickly, but with systematic uncertainties, or use distance indicators and survey thousands of galaxies slowly but more accurately. The cosmic microwave background offers another way to study voids, albeit indirectly. As photons from the cosmic microwave background travel through the universe, they pass through voids and clusters. As they enter a void, they fall into a shallow gravitational well, gaining energy and becoming slightly bluer. As they exit the void on the other side, they climb back out of the well, losing energy and becoming redder. If the void were static, these two effects would cancel out perfectly. But the universe is expanding, and as it expands, voids grow. By the time a photon exits a void, the void is larger and its gravitational well is shallower than when the photon entered. The photon doesn't lose as much energy climbing out as it gained falling in. The net result is a slight increase in the photon's energy. This is called the integrated Sachs-Wolf effect, and it creates a characteristic pattern in the cosmic microwave background. Regions of the sky that are slightly warmer where photons pass through voids. By mapping these temperature variations and correlating them with the positions of known voids, we can test our models of void structure and evolution. Studies have found evidence for this effect, confirming that voids do affect the cosmic microwave background in predictable ways. But the signal is weak, buried in noise and other effects, so extracting clear information about individual voids like the KBC void is challenging. There's a deeper philosophical question lurking here. How typical is our location in the universe? This isn't just idle curiosity. It's connected to the anthropic principle, the idea that we observe the universe to have certain properties because if it didn't have those properties, we wouldn't exist to observe it. For example, if the laws of physics were slightly different, stars might not form, or carbon might not be stable, or complex chemistry might be impossible, and life as we know it couldn't exist. So it's not surprising that we find ourselves in a universe where life is possible. We couldn't find ourselves anywhere else. Some scientists take this further and apply it to our location within the universe. Maybe we find ourselves in a void not because voids are common, but because voids are the kind of environment where life-bearing planets are more likely to form. Perhaps the isolation protects us from galaxy collisions or bursts of radiation from nearby supernovae or supermassive black holes. Perhaps the lower density makes it easier for planetary systems to remain stable over billions of years. This is speculative, bordering on science fiction, but it's not crazy. Location might matter for habitability in ways we haven't fully appreciated. Or maybe we're in a void for no reason at all, just cosmic bad luck, and we're reading too much into it. Let's return to the Hubble tension and explore some of the other proposed explanations that don't involve voids. One possibility is that the early universe was more complicated than our standard cosmological model assumes. Maybe there was an extra burst of radiation right after the Big Bang, or maybe neutrinos behave differently than we think, or maybe there were additional particle species present that have since decayed or become undetectable. These modifications to the early universe would change the patterns in the cosmic microwave background in subtle ways, potentially allowing for a higher Hubble constant while still matching the observed data. Another possibility involves dark energy. Maybe dark energy isn't constant. Maybe it was weaker in the past and has been getting stronger over time. This would affect the expansion history of the universe and could reconcile the different measurements of the Hubble constant. Observations of distant supernovae are starting to test this idea, looking for evidence that the expansion rate has changed over cosmic time. So far, the data is consistent with constant dark energy, but the uncertainties are still large enough to leave room for alternatives. Then there's the possibility that our measurements themselves are wrong. Not wrong in the sense of being careless or sloppy, but wrong in the sense that systematic errors we haven't accounted for are biasing the results. Distance measurements in astronomy are notoriously difficult. They require long chains of assumptions and calibrations, each step introducing potential errors. For example, to measure the distance to a supernova in a distant galaxy, we first need to measure the distance to nearby Cepheid variable stars using parallax, the apparent shift in a star's position as Earth orbits the Sun. Then we use those Cepheids to calibrate the brightness of Cepheids in more distant galaxies. Then we use those Cepheids to calibrate the brightness of type Ia supernovae, which can be seen at even greater distances. Each step in this cosmic distance ladder relies on the one before it, and errors can accumulate. Maybe metallicity, the abundance of elements heavier than hydrogen and helium, affects Cepheid brightness in ways we haven't fully accounted for. Maybe dust extinction, the dimming of light by interstellar dust, is more complicated than our models assume. Maybe type Ia supernovae aren't as standardizable as we think, and there are subtle variations we're missing. Any of these could introduce a bias that makes the universe seem to be expanding faster than it really is. Or maybe the cosmic microwave background measurements are the ones that need revision. The standard cosmological model, called lambda-CDM, has 6 free parameters: the density of normal matter, the density of dark matter, the dark energy density, the amplitude and tilt of primordial density fluctuations, and the optical depth to reionization. These parameters are fit to the cosmic microwave background data using sophisticated computer models that calculate what the microwave background should look like for different values of the parameters. The best fit model matches the data exquisitely well, but it's still a model and it rests on assumptions. Maybe there are additional parameters we haven't included, additional physics that affects the cosmic microwave background in ways we haven't considered. Maybe the universe underwent a phase transition or experienced some other event after the cosmic microwave background was released, something that altered the expansion history without leaving an obvious signature in the microwave background itself. These are speculative ideas, but they're being actively explored by cosmologists trying to make sense of the Hubble tension. Inflation, the period of exponential expansion thought to have occurred in the first fraction of a second after the Big Bang, might also play a role. Inflation solves several problems in cosmology: why the universe is so flat, why it's so uniform, and where the seeds of cosmic structure came from. During inflation, quantum fluctuations in the inflaton field, the field driving inflation, were stretched to cosmic scales and became the density variations that eventually grew into galaxies and clusters. But inflation is not a single, well-defined theory. It's a paradigm with hundreds of different models, each making slightly different predictions. Most models predict that inflation should leave a background of gravitational waves, ripples in spacetime that would imprint a particular pattern on the cosmic microwave background. Detecting this pattern is one of the holy grails of cosmology, and several experiments are searching for it. But inflation might also affect the Hubble constant. Some models predict that inflation lasted longer in some regions of space than others, creating variations in the expansion rate that persist to the present day. If we happen to be in a region where inflation lasted slightly longer, the local expansion rate could be different from the global average. This is similar to the void explanation, but operating on even larger scales and arising from very different physics. Time for a thought experiment. Imagine you're an astronomer living in a galaxy near the edge of the KBC void, right at the boundary where the void transitions into the surrounding denser regions. What would your view of the universe be like? Looking inward, toward the center of the void, you'd see very few galaxies, a sparse and lonely cosmos. Looking outward, away from the void, you'd see a rich tapestry of galaxies, clusters, and filaments, the full glory of the cosmic web. Your measurements of the Hubble constant would depend on which direction you looked. Looking inward, you'd measure a higher expansion rate, seeing galaxies recede more quickly in the low-density environment of the void. Looking outward, you'd measure a lower rate, seeing the gravitational drag of denser regions slowing the expansion. You'd realize that your location matters, that the universe doesn't look the same from every vantage point. You'd confront the same questions we're confronting now. How much does local structure affect measurements of global properties? How do we separate the signal from the noise, the cosmic average from the local peculiarity? And you'd probably feel a bit cheated, wishing you lived somewhere more representative, somewhere that offered a clearer view of the cosmos as it truly is. But maybe there's no such place. Maybe every location has its biases, its particular quirks that shape observations. Galaxy clusters see high densities and strong gravitational effects. Filaments see streaming motions as matter flows along the cosmic web. Voids see isolation and underdensity. Each environment offers a different perspective, and no single perspective is the true one. The universe is diverse, heterogeneous on small and intermediate scales, even as it's homogeneous on the largest scales. Understanding it requires stitching together observations from many locations, building a composite picture that transcends any single viewpoint. This is what modern surveys are trying to do. Observe galaxies in every environment, from the densest clusters to the emptiest voids, and use that comprehensive data set to infer the universe's properties. It's like mapping a mountain range by triangulating from multiple peaks. You need data from many locations to see the full shape of the terrain. The KBC void also raises questions about the future of the universe. Voids are expanding. As the universe grows older and expansion continues, voids will grow larger, encompassing more volume. Galaxies on the edges of voids will be pushed farther apart, and the interiors of voids will become emptier still. In the far future, billions of years from now, the Milky Way's view of the universe will change dramatically. Distant galaxies, already receding due to expansion, will move beyond our cosmic horizon, the distance beyond which light cannot reach us before it's redshifted into oblivion. Our descendants, if they exist, will see a lonelier cosmos with fewer galaxies visible in the night sky. The void around us will seem even vaster, and other voids will grow and merge, creating supervoids of unimaginable size. Eventually, in the unimaginably distant future, trillions upon trillions of years from now, the universe might consist of isolated islands of matter, remnants of galaxy clusters or superclusters, separated by voids so vast that no light or signal can ever cross them. It's a bleak picture, the heat death of the universe taken to its logical extreme. But it's also just a projection based on current understanding. Dark energy might change. The universe might surprise us. It has before. Let me tell you about one of the most remarkable aspects of void research. Despite their emptiness, voids are not structureless. Inside voids, matter still clumps, just more slowly and on smaller scales. Simulations show that voids contain a hierarchy of smaller voids within larger ones, a fractal-like structure that extends across multiple scales. These subvoids are where you find the sparsest regions, areas where even the faint filaments of dark matter peter out and true emptiness reigns. Some researchers have tried to define a void hierarchy, classifying voids by size and emptiness into categories like voids, mini-voids, and supervoids. The KBC void would be a supervoid in this scheme, one of the largest and emptiest structures known. But even within it, there are smaller voids, and within those, even smaller ones like Russian nesting dolls made of nothingness. This hierarchy arises naturally from the way gravity shapes matter. Large underdensities fragment into smaller underdensities, and those fragment further, creating a branching tree of emptiness that mirrors the branching tree of structure in denser regions. Galaxies inside voids are fascinating in their own right. They're laboratories for studying galaxy formation in isolation, free from the influences of neighbors and environment that complicate studies of galaxies in clusters or filaments. Void galaxies tend to have more gas and higher star formation rates relative to their mass, suggesting they're less evolved, younger in some cosmic sense. They're also bluer, indicating they have more young stars and fewer old, red stars. This makes sense. In a void, there are fewer opportunities for interactions with other galaxies, fewer mergers that can trigger bursts of star formation or consume gas. Void galaxies live slower, quieter lives, accumulating mass gradually from the sparse gas around them rather than through violent collisions. Some are almost perfectly pristine, galaxies that have never experienced a major merger or interaction, preserving the conditions of their birth billions of years ago. Studying these galaxies can tell us what the early universe was like, before galaxies had time to interact and evolve into the complex, messy objects we see in denser environments. They're time capsules, windows into a simpler era of cosmic history. There's also the question of how galaxies end up in voids in the first place. Did they form there in situ, condensing out of the sparse gas available in the void? Or did they form elsewhere and drift into the void over time? The answer is probably both. Some void galaxies likely formed right where they are, in the rare pockets of density that existed in underdense regions. These would be small galaxies, limited by the amount of matter available to build them. Other void galaxies, especially the larger ones like the Milky Way, if we accept that we're truly inside the void, probably formed in denser regions and migrated. Galaxies are not stationary. They move through space, pulled by the gravity of nearby structures. A galaxy that forms near the edge of a forming void might find itself gradually drifting inward as the void expands and pushes matter toward the walls. Or a galaxy might be ejected from a cluster by a gravitational interaction, thrown out into the void like a ball launched from a cannon. These ejected galaxies would carry with them the characteristics of their birthplace, making them stand out in the void population. They'd be larger, redder, more massive than typical void galaxies, and their presence would be a clue to their origin. The cosmic web, with its filaments and voids, is not static. It's constantly evolving, driven by gravity. Filaments grow denser as matter flows into them. Clusters at the intersections of filaments grow more massive, consuming smaller galaxies and groups. And voids expand, pushing matter out toward the filaments and clusters. This is a slow process, taking billions of years to produce noticeable changes. But it's happening. Simulations of cosmic evolution show that the universe becomes more structured over time, with denser regions becoming denser and emptier regions becoming emptier. This is called gravitational instability, and it's a fundamental feature of how gravity works. Any small difference in density, no matter how tiny, will grow over time because denser regions attract more matter, making them denser still, which attracts even more matter in a runaway process. The only thing that stops this process is expansion. The universe is expanding, which dilutes matter and reduces the strength of gravity. In regions where expansion dominates, structure formation stops and voids just keep growing. In regions where gravity dominates, expansion is overcome and structures collapse, forming clusters and galaxies. Dark energy accelerates expansion, and this has profound implications for structure formation. Before dark energy began to dominate roughly 5 billion years ago, the universe was decelerating. Expansion was slowing down, held back by the gravity of all the matter in the universe. In this environment, structure formation could proceed relatively unhindered. Matter clumped efficiently, building the cosmic web we see. But as dark energy took over and expansion began to accelerate, structure formation became harder. Expansion now carries matter apart faster than gravity can pull it together, except in regions that are already very dense and have collapsed into bound structures. This means that the largest structures in the universe, things like galaxy clusters and superclusters, are probably done forming. They're as large as they're going to get, barring the occasional merger when two clusters happen to collide. Future generations of astronomers will inherit a universe where the large-scale structure is frozen, a static tapestry that no longer evolves. Voids, meanwhile, will continue to expand, growing ever emptier as the few remaining galaxies inside them drift toward the void walls. Let's zoom way out to the largest scales observable in the universe. The cosmic horizon, the edge of the observable universe, is about 46 billion light-years away in all directions. That's the distance to the farthest objects we can see, the ones whose light has been traveling toward us since the Big Bang. Beyond that horizon, there's more universe, but we can't see it because light from those regions hasn't had time to reach us yet. The universe is only 13.8 billion years old, and light can only travel so far in that time. Every day, as the universe ages, our horizon expands and we can see slightly farther. But because the universe is also expanding, distant objects are receding from us, and some will cross the horizon in the opposite direction, moving away so fast that their light will never reach us. The interplay between these effects creates a complicated, evolving view of the cosmos. Now, here's the staggering part. The observable universe contains roughly 2 trillion galaxies. 2 trillion. And the KBC void, as large as it is a tiny fraction of that. It occupies maybe a billionth of the total volume of the observable universe, which means that even if we're in an atypical location, statistically speaking, there are billions of other regions just as atypical elsewhere in the cosmos. Voids like the KBC void are rare, but they're not unique. There are other supervoids out there, other vast expanses of emptiness where other galaxies sit, perhaps wondering the same questions we're wondering. The question of typicality connects to a concept called the Copernican principle, named after Copernicus, who argued that Earth is not the center of the universe. The Copernican principle, in its modern form, states that we should not assume we occupy a special or privileged position in the universe. We're not at the center. We're not in an unusual location. We're typical, average, unremarkable. This principle has been enormously successful in science. It led to the realization that the Sun is just one star among billions, that the Milky Way is just one galaxy among billions, that there's nothing cosmically significant about our location. But the KBC void challenges this principle. If we're in a supervoid, we are in an unusual location, at least on scales of hundreds of millions of light years. Not unique, but atypical. Does this violate the Copernican principle? Not necessarily. The principle applies to the largest scales, and on those scales, the universe does appear homogeneous and isotropic. Voids and clusters are just local variations, statistical fluctuations in an otherwise uniform cosmos. The Copernican principle says that if you zoom out far enough, everyone sees the same universe. And that still seems to be true. The cosmic microwave background looks the same in all directions. The distribution of galaxy clusters is statistically uniform on large scales, and the expansion of the universe is isotropic. We're in a void, but voids are a normal part of cosmic structure, so being in one doesn't make us special. It just makes us locally atypical, which is different. There's an intriguing connection between voids and the formation of the first stars and galaxies in the universe. The early universe, just a few 100 million years after the Big Bang, was dark. The cosmic microwave background had cooled into invisibility. Stars hadn't formed yet, and the universe was filled with neutral hydrogen gas. Then, slowly, the first stars ignited, burning hydrogen in nuclear fusion and flooding their surroundings with ultraviolet light. This light ionized the hydrogen, splitting it into protons and electrons, creating bubbles of ionized gas around each star. As more stars formed, these bubbles grew and merged, eventually ionizing all the hydrogen in the universe in a process called reionization. Voids played a role in this. The first stars formed preferentially in overdense regions, places where there was enough matter to collapse and ignite fusion. Voids, being underdense, lagged behind. They were the last places to be ionized, the last regions where neutral hydrogen persisted. By studying voids today, we can learn about the end stages of reionization and how it proceeded in the least dense environments. Some voids might even contain pockets of neutral hydrogen that survive to the present day, relic clouds that never got ionized. Detecting these would be a major discovery, a window into the universe's adolescence. Fast radio bursts. Let me take a detour to talk about fast radio bursts, or FRBs, because they're relevant to void science in a surprising way. FRBs are intense, millisecond duration pulses of radio waves that come from distant galaxies. They were first discovered in 2007, and they've been one of the biggest mysteries in astronomy ever since. We don't know for certain what causes them, though neutron stars, specifically highly magnetized neutron stars called magnetars, are the leading candidates. What makes FRBs interesting for void research is that as their radio waves travel through space, they interact with free electrons in the intergalactic medium. The denser the medium, the more the radio waves are delayed, an effect called dispersion. By measuring the dispersion of an FRB and knowing the distance to its host galaxy, we can infer the average density of electrons along the line of sight. If the line of sight passes through a void, the dispersion will be lower than average because there are fewer electrons. Conversely, if it passes through a dense region, dispersion will be higher. By studying many FRBs coming from different directions, we can start to map the distribution of matter in the intergalactic medium, including voids. It's like cosmic tomography using radio bursts to probe the structure of space. This is still a developing technique, but as we discover more FRBs and measure them more precisely, it could become a powerful tool for studying voids and their properties. Gravitational waves offer another new avenue for probing voids. Gravitational waves are ripples in spacetime caused by violent events like the collision of black holes or neutron stars. The Laser Interferometer Gravitational Wave Observatory, LIGO, and its counterpart Virgo have been detecting these waves since 2015, opening an entirely new window on the universe. Gravitational waves travel at the speed of light, and like light, they're affected by the matter they pass through. As a gravitational wave crosses a void, it experiences less lensing and distortion than it would crossing a dense region. By measuring the properties of gravitational waves and comparing them to what we expect based on their sources, we might be able to infer the presence of voids or other large-scale structures along the line of sight. This is speculative at the moment. Gravitational wave astronomy is still in its infancy, and the measurements aren't yet precise enough to do this kind of analysis. But as detectors improve and we build more of them, including space-based detectors like LISA, the Laser Interferometer Space Antenna, planned for launch in the 2030s, gravitational wave cosmology could become a reality. Imagine mapping the universe not with light, but with gravity itself. It's an exciting prospect. Let's address a common misconception. Voids are not vacuums in the sense of having zero pressure or zero matter. They're not regions where the laws of physics stop working or where space is somehow fundamentally different. They're just regions with less stuff. The difference between a void and an average region of space is quantitative, not qualitative. An average region might have 1 galaxy per cubic megaparsec, while a void might have 1 galaxy per 10 cubic megaparsecs. That's significant in terms of density, but it's not a different kind of space. Light travels through voids the same way it travels through dense regions. Gravity works the same. Quantum mechanics applies. The electromagnetic force hasn't changed. Voids are normal space with less matter in it, and that's all. This is worth emphasizing because popular descriptions of voids sometimes make them sound exotic or mysterious, as if they're holes in reality. They're not. They're just empty neighborhoods in the cosmic city, places where the buildings are farther apart and the streets are wider. If you could somehow travel into a void, you wouldn't notice anything unusual unless you were an astronomer with a telescope. The sky would look darker, with fewer galaxies visible, but otherwise everything would be normal. Speaking of travel, let's have some fun with numbers. Suppose you wanted to cross the KBC void. You're starting from the Milky Way near the center, and you want to reach the edge, roughly 500 million light-years away. If you could travel at 1% the speed of light, which would require technology far beyond anything we currently have, it would take you 50 billion years to make the journey. That's more than 3 times the current age of the universe. Even at 10% the speed of light, a staggering velocity that would require enormous energy, the trip would take 5 billion years. By the time you arrived, the sun would have died, the Earth would be long gone, and the Milky Way would have collided with Andromeda. Faster-than-light travel is prohibited by relativity, but even if it weren't, you'd still face the problem that the void is expanding. The edge of the void is receding from us due to the expansion of space. Depending on how fast that expansion is, you might never catch up, even traveling at near light speed. You'd be like someone running on a treadmill that's accelerating faster than you can run. This is one reason why the universe is so profoundly isolating. The distances are not just large, they're insurmountable. Philosophically, voids remind us of scale. Humans are terrible at grasping large numbers and vast distances. We evolved to navigate environments measured in kilometers, not light years. Our brains didn't evolve to comprehend a void a billion light years across. Yet here we are, using those same brains, those same neurons that helped our ancestors track game and find water, to map the structure of the cosmos. It's remarkable. We've extended our senses with telescopes and detectors, our minds with mathematics and computers, and we've built up a picture of the universe that would have been unimaginable to anyone living just a century ago. And we've discovered that we live in a strange place, an emptier-than-average corner of a vast and diverse cosmos. That's humbling. Puts our everyday concerns in perspective. Your worries, my worries, all the noise and chaos of human life. It's all happening on a tiny planet, orbiting an average star in an unremarkable galaxy, sitting in a great big cosmic void. We're specks of dust in an empty room in an incomprehensibly large house. And yet we're the dust that can think, that can wonder, that can figure out where we are and what it means. This brings me to the question of existential risk. Does living in a void put us at any greater risk than we'd face elsewhere in the universe? The short answer is no. Voids are actually safer than dense regions in some respects. Galaxy clusters, with their tightly packed galaxies, experience more collisions and interactions. Active galactic nuclei, supermassive black holes feeding on matter and spewing radiation, are more common in dense environments. Supernovae and gamma-ray bursts, while rare, are more frequent where star formation is vigorous, which tends to be in denser regions. Voids, by contrast, are quiet. The Milky Way sits in relative isolation, far from any major cluster, far from any nearby galaxy capable of disrupting us gravitationally. Andromeda is coming, yes, but that's billions of years away, and the collision, when it happens, will be more of a merger than a crash. Stars are so far apart that individual stellar collisions are vanishingly unlikely. We might actually be safer in this void than we would be in a busier neighborhood. The main risk of living in a void is epistemic, not physical. It affects what we can learn about the universe, not whether we survive. And even that risk is manageable. We can correct for our location. We can build better models. We can search for better data. Science is self-correcting. Given enough time and effort, we'll figure it out. There's a lovely irony in all this. We live in an age where we can see nearly to the edge of the observable universe. We can detect light from galaxies so distant that it was emitted when the universe was less than 1 billion years old. We can measure the cosmic microwave background, light that has been traveling for 13.8 billion years, to exquisite precision. We've mapped millions of galaxies, traced the cosmic web, and measured the expansion of the universe. And yet, despite all this, we're uncertain about our own cosmic address. We think we're in a void, but we're not entirely sure how big it is or how underdense it is or what its boundaries are. We've looked out at the entire observable universe, and we've gotten a bit confused about our own backyard. That's the nature of astronomy. The farther you look, the clearer things become in some ways. Distant galaxies obey simple, predictable laws. They're moving away from us in a uniform Hubble flow, their properties averaging out over cosmic scales. But nearby, things are messy. Peculiar motions, local gravitational influences, and environmental effects complicate everything. It's easier to understand the forest than the individual trees, easier to grasp the universe as a whole than the particular quirks of our neighborhood. But understanding both is essential. We need the big picture to make sense of the details, and we need the details to test whether the big picture is right. Now, let's consider what happens if the void explanation for the Hubble tension is wrong. If better data comes in and shows that the void can't account for the discrepancy, what then? We'd be back to square one, searching for an explanation. And that might be exciting because it would mean our physics is incomplete in interesting ways. Maybe general relativity needs modification on cosmological scales. Einstein's theory has passed every test we've thrown at it, from GPS satellites to black hole mergers, but we've never tested it on scales of billions of light years with the precision we're now demanding. Maybe there's a subtle correction needed, a term we've been neglecting that becomes important at those scales. Or maybe it's not gravity that needs fixing, but our understanding of particle physics. Maybe there are additional particles or forces we haven't discovered yet, ones that affect the universe's expansion in ways we can't currently predict. This wouldn't be the first time observations forced us to extend our theories. Dark matter was inferred from observations that couldn't be explained by known physics. Dark energy was discovered because supernovae weren't behaving as expected. Each time, the universe surprised us, and each time we rose to the challenge and expanded our understanding. The Hubble tension might be the next such surprise, a clue that there's more to learn, new physics waiting to be uncovered. There's also the possibility that both measurements are right, but they're measuring different things. What if the Hubble constant actually varies with position in the universe, not just because of local structure like voids, but because the universe itself is not perfectly homogeneous on the scales we're probing? This would be a radical departure from the cosmological principle, the foundational assumption that the universe is the same everywhere. But maybe it's only approximately true. Maybe there are large-scale variations in the expansion rate, remnants of the early universe or effects of quantum fluctuations during inflation that create different expansion rates in different regions. We might be in a region where the expansion is faster than average, and observers in other regions would measure different values. If this is true, there wouldn't be a single Hubble constant. There would be a distribution of values, and the true Hubble constant would be some kind of average that no individual observer ever measures directly. This sounds crazy, and it would require rethinking a lot of cosmology, but it's not ruled out by current data. It's an idea on the fringe, not widely accepted, but worth keeping in mind as observations improve. Let me bring in some recent developments. In 2019, a team led by Valentine Rubin analyzed data from the Dark Energy Survey and found hints that the expansion rate might vary with direction. When they measured the Hubble constant using supernovae in different parts of the sky, they got slightly different answers. The differences were small, within the uncertainties, but they were suggestive. If real, this would imply that the universe's expansion is not perfectly isotropic, that it's expanding faster in some directions than others. This would be shocking, a major violation of the cosmological principle. Other teams have looked for the same effect and haven't seen it, or they've seen it but with different patterns that don't match. So the jury's still out. It might be a statistical fluctuation. It might be systematic errors. Or it might be real, a sign that the universe is more complex than we thought. More data will clarify things. The Rubin Observatory, when it comes online, will observe millions of supernovae and provide the statistical power needed to test these ideas definitively. Another recent development involves something called the Boss Great Wall, an enormous supercluster of galaxies about 1 billion light-years long. It's one of the largest known structures in the universe, a vast concentration of matter that forms a wall of galaxies stretching across a huge swath of space. Structures like this challenge our understanding of how the universe forms. Standard models of structure formation predict that there's a maximum size for gravitationally bound structures, set by the age of the universe and the strength of gravity. The Boss Great Wall is close to that maximum, perhaps even exceeding it depending on how you measure. If structures this large are common, it would suggest that the universe is more heterogeneous than we think, with variations in density persisting on much larger scales than predicted. And if the universe is more heterogeneous, our assumptions about homogeneity and isotropy might need revision, which would affect everything from the interpretation of the cosmic microwave background to the measurement of the Hubble constant. We should also talk about observational biases. Astronomy is observational, not experimental. We can't set up controlled experiments on cosmic scales. We can only observe what the universe presents to us, and we have to work backward from those observations to infer the underlying reality. This creates opportunities for biases to creep in. Selection effects are one example. We tend to discover the brightest, most dramatic objects because they're the easiest to see. Faint, diffuse objects get overlooked. This means our catalogs of galaxies are biased toward the bright end, and our understanding of the galaxy population might be skewed. Measurement biases are another problem. Every instrument has systematic errors, and correcting for them requires careful calibration. If we make a mistake in calibration, it can propagate through all our measurements, creating false signals or hiding real ones. Then there are theoretical biases. We interpret observations using models, and if our models are wrong, our interpretations will be wrong too. The void interpretation of the Hubble tension is itself a model, one that makes certain assumptions about how voids affect measurements. If those assumptions are flawed, the interpretation is flawed. Let's imagine a future scenario. It's 2045. The Rubin Observatory has been operating for 20 years, cataloging billions of galaxies and mapping the cosmic web in unprecedented detail. The James Webb Space Telescope has been joined by even larger, more powerful successors in space. Gravitational wave astronomy is routine, with dozens of detectors operating around the world and in orbit. Fast radio bursts are detected daily and used for tomography of the intergalactic medium. And finally, after decades of debate, the Hubble tension is resolved. The answer turns out to be a combination of factors. The KBC void does contribute to the discrepancy, accounting for 2 or 3 kilometers per second per megaparsec of the difference. Systematic errors in distance measurements, subtle effects not properly accounted for, explain another 2. And the remaining difference? New physics, a slight modification to general relativity, or an additional component of dark energy, or some other effect we hadn't considered. The result is a richer, more complex picture of the cosmos, one that incorporates everything we've learned and points the way to new discoveries. This is how science works, not in sudden revolutions, but in gradual accumulation of knowledge, each answer raising new questions, each mystery resolved revealing deeper mysteries beneath. We're living in a golden age of cosmology. A century ago, we didn't even know other galaxies existed. We thought the Milky Way was the entire universe. Then Hubble discovered that those fuzzy nebulae in the sky were actually galaxies, each containing billions of stars, and the universe suddenly became unimaginably larger. 50 years ago, we discovered the cosmic microwave background, proof of the Big Bang, and we started to understand the universe's history. 25 years ago, we discovered dark energy and realized the universe's expansion is accelerating, changing our predictions about cosmic fate. And now, we're grappling with the Hubble tension and the realization that we might live in a void, that our local measurements might not reflect the cosmic average. Each discovery expands our horizons and challenges our assumptions. And each challenge is an opportunity to learn something new, to refine our theories, to get closer to the truth. That's the beauty of science. The self-correcting, always moving forward, always striving for better answers. Let me address one more common question. Could we ever leave the void? If we achieved interstellar travel, if we somehow developed the technology to cross the distances between stars and then galaxies, could we visit the denser regions of the universe? The answer is theoretically yes, but practically no. The distances are simply too vast. The nearest large galaxy cluster, the Virgo cluster, is about 50 million light-years away. Even traveling at the speed of light, which is impossible, it would take 50 million years to get there. With realistic propulsion technologies, ones based on known physics, it would take billions or trillions of years. By the time we arrived, the stars we left behind would be dead, the galaxies unrecognizable. Interstellar travel within the Milky Way is already a monumental challenge, requiring either generation ships that could sustain human populations for thousands of years or some kind of suspended animation technology that doesn't yet exist. Intergalactic travel is orders of magnitude harder. The void, for all practical purposes, is our home forever. We will never see its far shores, but we can see them with our telescopes. We can map the void, study its properties, understand its effects. We can look beyond the void to the filaments and clusters that surround it, comparing galaxies in different environments and learning how location shapes evolution. We can use the void as a natural laboratory, a cosmic control experiment where we see how galaxies behave in isolation. And we can use our position in the void to learn about the universe itself, correcting for our local peculiarities and inferring what the cosmos looks like from a more average vantage point. Being in the void is not a limitation. It's an opportunity. It gives us a unique perspective, one that complements observations from other locations and helps build a more complete picture of reality. Every observer sees the universe slightly differently, and by combining observations from many observers, real and hypothetical, we can triangulate on the truth. There's a certain poetry to living in a void. Humanity has always felt alone, isolated on our pale blue, in the vastness of space. And now we learn that we're even more isolated than we thought, sitting in an enormous bubble of emptiness, separated from the main hubs of galactic activity by hundreds of millions of light-years of near-nothingness. It reinforces the sense that we're on our own out here, that if we're going to survive and thrive, we have to do it ourselves. There's no galactic federation coming to save us, no nearby civilizations to trade with or learn from, just us alone in the void. But isolation has its advantages. It's given us time to develop, to evolve, to build a civilization without interference. It's kept us safe from the chaos and violence of denser regions. And it's given us this incredible view of the universe, a view we might not have had elsewhere. Maybe being in the void is a gift. Maybe it's exactly where we need to be. As we approach the conclusion of this journey through cosmic emptiness, I want to emphasize one final point. The KBC void and the questions it raises are not just academic curiosities. They're central to our understanding of the universe and our place in it. The Hubble tension might seem like a technical problem, a disagreement about a single number, but it goes deeper than that. It's about whether we truly understand the universe's history, its present, and its future. It's about whether our physics is complete or whether there are gaps waiting to be filled. It's about whether our observations are reliable or whether we're being deceived by our location. These are fundamental questions, ones that will shape the direction of cosmology for decades to come. And the answers, whatever they turn out to be, will change how we think about the cosmos and our place within it. So what's the conclusion? What's the takeaway from all this? Here it is. We live in a huge void, a billion light-year bubble of relative emptiness in the cosmic web. This void might be affecting our measurements of the universe's expansion rate, creating a discrepancy between local measurements and predictions from the cosmic microwave background. Or it might not. The data isn't conclusive yet. We need better measurements, more precise instruments, and more sophisticated models to figure out what's really going on. But regardless of whether the void explains the Hubble tension, it's a fascinating feature of our cosmic neighborhood, one that affects our view of the universe and challenges our understanding of cosmic structure. Being in the void doesn't make us special or privileged. It makes us atypical, which is different, and that's okay. The universe is vast and diverse, full of different environments and perspectives. We happen to be in one of the emptier neighborhoods, and that's shaped what we see and how we interpret it. The problem isn't that we're in a void. The problem is that we didn't know it for so long, and we've been making measurements without accounting for it. Now that we know, we can start to correct for it. We can ask better questions. We can design better experiments. We can build a more accurate picture of the cosmos. Science is a process, not a destination. We're always learning, always revising, always getting closer to the truth. The void is just the latest challenge, the latest puzzle to solve. And we will solve it. Maybe not tomorrow, maybe not next year, but eventually. That's what humans do. We figure things out. We're the species that looked up at the stars and wondered what they were, that built telescopes to see farther, that developed mathematics and physics to understand what we were seeing. We're the species that went from thinking Earth was the center of everything to realizing we're in a void in a universe so vast we can barely comprehend it. And we did it in just a few centuries, an eye blink in cosmic time. So yes, we're living inside a huge void. Yes, there's a problem. It might be distorting our measurements and confusing our understanding. But problems are opportunities. They're invitations to dig deeper, to question assumptions, to expand knowledge. The void isn't an obstacle. It's a teacher. It's showing us that the universe is more subtle and complex than we thought, that location matters, that local isn't always representative of global. These are important lessons, ones that will inform cosmology for generations to come. And as we learn them, as we figure out how to account for the void and measure the universe more accurately, we'll be writing the next chapter in humanity's ongoing story of cosmic discovery. A story that began in caves and on savanna plains, continued through observatories and laboratories, and now reaches out into the void itself, seeking to understand the largest, most fundamental features of reality. We're living in a void, but we're not lost. We're exactly where we need to be, doing exactly what we were meant to do. Wondering, questioning, exploring, and trying to understand the strange, beautiful, incomprehensible universe we call home. Let me take you deeper into something we haven't fully explored: what happens at the boundaries of voids. Because voids don't just end, they transition. There's a gradient, a cosmic shoreline where emptiness gives way to structure. These boundary regions, called void walls, are among the most interesting environments in the universe. They're where matter has been pushed by the expansion of the void, compressed and concentrated like foam gathering at the edge of a bubble. Galaxy formation in these walls proceeds differently than in the void interior or in dense clusters. The walls receive a steady stream of matter draining from the void, feeding star formation and galactic growth. Some of the most massive spiral galaxies in the universe live on void walls, gorging themselves on this influx of gas and dark matter. The dynamics at these boundaries are complex. Imagine standing on a beach watching waves. The water rushes in, then pulls back out. Void walls experience something similar, but over cosmic timescales. Matter flows outward from the void center toward the walls, then gets captured by the gravitational pull of forming structures in the walls. This creates a feedback loop. As structures in the wall grow more massive, they pull harder on matter in the void, accelerating the drainage. The void becomes emptier, the walls become denser, and the contrast between them sharpens. Eventually, the void reaches an equilibrium of sorts, where the outward push of expansion balances the inward pull of gravity from surrounding structures. But this equilibrium is temporary. Dark energy keeps pushing, and the void keeps growing, just more slowly. Now consider the magnetic fields. We don't talk enough about magnetic fields in cosmology because they're notoriously difficult to measure. But they're there, threading through the cosmos, carried by charged particles in the intergalactic medium. In dense regions, magnetic fields are strong, amplified by the compression of matter and the dynamo effects of rotating galaxies. In voids, magnetic fields are weak, stretched thin by expansion. Measuring these fields requires looking at radio waves from distant sources and seeing how they're polarized as they pass through magnetized plasma. Recent surveys have started doing this, mapping the magnetic structure of the cosmic web. What they're finding is fascinating. Even in voids, there are magnetic filaments, ghostly threads of field lines that trace the dark matter skeleton. These fields are incredibly weak, billions of times weaker than Earth's magnetic field, but they're present, and they might play a role in shaping how gas flows through voids, channeling it along field lines like water flowing through irrigation channels. Let's talk about void statistics. How many voids are there? What's their size distribution? These questions might sound dry, but they're crucial for testing our models of cosmic structure. If we understand how voids form and evolve, we can predict how many voids of different sizes should exist. Then we compare predictions to observations. Current surveys have identified thousands of voids, ranging from small mini-voids 30 million light-years across to supervoids over 1 billion light-years wide. The distribution follows a power law. Small voids are common, large voids are rare. This matches what simulations predict, which is reassuring. It suggests our models of structure formation are on the right track. But there are discrepancies. Some surveys find more large voids than expected, or voids that are emptier than simulations produce. These mismatches could be statistical flukes, or they could be hints that something in our models needs adjustment. Maybe the initial conditions we use for simulations aren't quite right. Maybe dark energy behaves differently than we assume. Or maybe there's a systematic bias in how we identify voids from observational data. Speaking of identification, how do you actually define a void? It sounds simple, a region with fewer galaxies than average. But in practice, it's tricky. Do you count by number of galaxies or by total mass? Do you include dark matter or just visible matter? How do you draw the boundaries? Different research groups use different definitions, which leads to different void catalogs that don't always agree. Some algorithms look for spherical underdensities, others trace out irregular shapes that follow the natural contours of the cosmic web. Some definitions are based on galaxy counts, others on the gravitational potential field. This might seem like academic hair-splitting, but it matters. When you're trying to compare observations to simulations, or studying how void properties correlate with other cosmic phenomena, you need consistent definitions. The community is working toward standardization, developing consensus criteria for what counts as a void. But we're not there yet. Consider the evolution of void galaxies over cosmic time. The galaxies we see in voids today are snapshots of their current state, but they have histories. They formed billions of years ago, evolved through mergers and star formation, and arrived at their present configuration. By looking at galaxies at different distances, which means different times in cosmic history because of light travel time, we can reconstruct this evolution. What astronomers have found is that void galaxies were different in the past. Billions of years ago, when the universe was younger, voids were less empty. They contained more galaxies, more gas, more star formation. As the universe aged and structure continued to form, these galaxies either drifted out toward void walls or used up their gas supplies and stopped making stars. The voids became quieter, emptier, more like the hushed spaces we observe today. This evolution matches predictions, but with surprises. Some void galaxies show bursts of recent star formation, unexpected flares of activity that suggest they acquired fresh gas somehow, perhaps from a minor merger or from gas flowing in along dark matter filaments. There's an entire subfield devoted to what are called void probabilities, the mathematical functions that describe the likelihood of finding a void of a given size at a given location. These functions are sensitive to cosmological parameters, things like the matter density, the dark energy equation of state, and the amplitude of primordial fluctuations. By measuring void probabilities observationally and comparing them to theoretical predictions, cosmologists can constrain these parameters. It's another way to test our models, independent of other methods like supernova observations or cosmic microwave background analysis. The results so far have been broadly consistent with standard cosmology, but the error bars are still large. As surveys improve and we map more voids more accurately, these constraints will tighten. Void statistics might become one of the premier tools for precision cosmology, sitting alongside better-known methods as a pillar of our understanding. Let me introduce you to the concept of void hierarchy. Voids within voids within voids, like Russian dolls. This isn't just a metaphor. Simulations show that the underdense regions of the universe have self-similar structure across multiple scales. A large void contains smaller voids, and those contain even smaller ones, down to scales where individual galaxy interactions become important and the smooth assumptions of cosmology break down. This fractal-like structure arises naturally from gravitational dynamics. When matter collapses to form structure, it leaves behind increasingly refined patterns of emptiness. The largest voids formed first, seeded by the largest underdensities in the early universe. Within those, smaller underdensities led to smaller voids, and so on. This hierarchy has implications for how we interpret observations. When we identify a void in a survey, are we seeing a single coherent structure, or a family of nested voids that we're lumping together because we lack the resolution to distinguish them? The answer depends on the void size and our survey's depth. Cosmic rays present an interesting puzzle related to voids. Cosmic rays are high-energy particles, mostly protons, that zip through space at nearly the speed of light. They're produced by supernovae, active galaxies, and other violent events. When cosmic rays travel through space, they interact with photons from the cosmic microwave background and starlight, losing energy in the process. This limits how far they can travel before degrading. The most energetic cosmic rays, called ultra-high-energy cosmic rays, can only come from relatively nearby sources, within a few hundred million light-years. But when we trace back the trajectories of detected ultra-high-energy cosmic rays, trying to identify their sources, we don't find obvious candidates. There aren't enough active galaxies or powerful supernovae in our cosmic neighborhood to account for all the cosmic rays we see. Could the void be relevant? Some researchers think so. In a void, cosmic rays travel farther before interacting because there's less matter and fewer photons to collide with. A cosmic ray that would degrade in 100 million light-years in a dense region might survive 300 million light-years in a void. This extends the possible source region, potentially resolving the mystery. But it's still speculative and other explanations exist. Temperature gradients across voids are subtle but real. The intergalactic medium, the diffuse gas between galaxies, has a temperature determined by heating from stars and cooling from expansion. In dense regions, heating dominates because there are more stars and more violent processes. Gas temperatures can reach millions of degrees. In voids, cooling wins. There are fewer stars, less feedback from supernovae and black holes, and the gas cools as space expands. Typical void gas is around 10,000 degrees, warm by terrestrial standards but cool by cosmic ones. This temperature difference affects what we can observe. Hot gas emits X-rays, which we can detect with space-based X-ray telescopes. Cool gas doesn't emit much, making it harder to study. Most of our knowledge about the intergalactic medium comes from dense regions where the gas is hot and bright. Void gas is largely invisible, inferred indirectly from its absorption of light from background sources. We know it's there because distant quasars, bright beacons powered by supermassive black holes, show absorption lines in their spectra where intervening gas has absorbed specific wavelengths. By studying these absorption lines, we can map the gas distribution along the line of sight, including gas in voids. Let's discuss void lensing. Gravitational lensing, where mass bends light, is usually associated with massive objects like galaxy clusters or black holes. But voids also lens, just in the opposite sense. A void is an underdensity, a deficit of mass, which creates a gravitational defocusing. Light passing through a void spreads out slightly rather than converging. This makes background objects appear fainter and slightly larger than they would without the void. The effect is tiny, less than 1% for most voids, but measurable with sensitive instruments. By studying how light from distant galaxies is defocused by foreground voids, we can map the mass distribution in the void, including dark matter. It's a way to weigh voids, determining not just how few galaxies they have, but how much total mass they contain. Early attempts at void lensing have been challenging because the signal is so weak. It requires stacking data from many voids to detect anything. But as surveys grow and statistical power increases, void lensing will become a standard tool. The connection between voids and the cosmic microwave background goes beyond the integrated Sachs-Wolf effect I mentioned earlier. There's also a phenomenon called the Rees-Sayama effect, named after Martin Rees and Dennis Sayama, who predicted it in the 1960s. When cosmic microwave background photons pass through a time-varying gravitational potential, they gain or lose energy depending on whether the potential is deepening or shallowing. In a collapsing structure like a forming galaxy cluster, the potential deepens and photons lose energy. In an expanding void, the potential shallows and photons gain energy. Both effects create temperature fluctuations in the cosmic microwave background, but their secondary effects much smaller than the primordial fluctuations from the early universe. Detecting the Rees-Sayama effect requires incredibly precise measurements and careful subtraction of other signals. Only recently have we started seeing hints of it in the data. As measurements improve, the Risayama effect could provide another independent test of our cosmological models and our understanding of how structure evolves. Now let's venture into more speculative territory. Some physicists have proposed that voids might be laboratories for detecting modifications to general relativity. Einstein's theory works brilliantly in strong field regimes like around black holes, and in weak field regimes like the solar system. But on cosmic scales, in extremely weak gravitational fields like those in voids, maybe general relativity needs corrections. These corrections would be tiny, undetectable in denser environments, but potentially observable in voids where gravity is at its weakest. Testing this requires comparing how light and gravitational waves travel through voids versus through dense regions. Any discrepancy could signal new physics. Several modified gravity theories predict such discrepancies. Theories like F.R. gravity, scalar tensor theories, and massive gravity all make slightly different predictions about how gravity behaves in weak field environments. Voids are where these theories diverge most from standard general relativity, making them ideal testing grounds. But the signals are subtle, and we need better observational precision before we can say anything definitive. There's also the question of primordial voids. Most voids formed through the gravitational evolution of structure over billions of years. But some physicists speculate that certain voids might have different origins, formed by processes in the very early universe. For example, if the universe underwent phase transitions during its first moments, when quantum fields settled into their current states, these transitions might have created regions with different properties. Bubbles of different phases could have formed, expanded, collided. Some might have become voids, regions where the phase transition proceeded differently and left behind an underdensity that persisted to the present. This is highly speculative, but not impossible. If primordial voids exist, they'd have distinctive signatures, sharper boundaries, different internal structure, possibly unusual distributions of dark matter. Searching for these signatures is an active area of research, though so far nothing conclusive has emerged. The role of neutrinos in voids deserves attention. Neutrinos are ghostly particles, produced in vast numbers by the sun and other stars, that barely interact with matter. They stream through space at nearly the speed of light, and because they have tiny masses, they contribute to the overall matter budget of the universe. In the early universe, neutrinos were relativistic, moving so fast that their gravity couldn't clump matter effectively. This delayed structure formation on small scales, suppressing the growth of low-mass objects. In voids, where structure formation is already slow, this neutrino suppression is more pronounced. The result is that voids in a universe with massive neutrinos are slightly different from voids in a universe with massless neutrinos. They're emptier with fewer small galaxies. By studying the galaxy population in voids, we can constrain the total mass of neutrinos, providing an independent measurement that complements laboratory experiments and cosmological observations. Current constraints from void studies are weak, but as data improves, voids might become one of the best ways to measure neutrino mass. Let's talk about the cosmic web itself in more detail. The web is not a static structure. It's dynamic, evolving, with matter flowing along filaments like traffic on highways. Simulations show that gas flows from voids into filaments at velocities of hundreds of kilometers per second, then channels along the filaments toward nodes where clusters form. This flow is driven by gravity, but it's also affected by pressure, magnetic fields, and the expansion of space. In voids, the flow is slow and smooth. In filaments, it accelerates and becomes turbulent. At nodes, it collides with flows from other filaments, creating shocks and heating the gas to extreme temperatures. This whole system is a cosmic circulation, redistributing matter over billions of years. Voids are the low-pressure zones, the places where matter drains away. Understanding this circulation is key to understanding how galaxies form and evolve, because galaxies are built from gas that flows through the web. A galaxy forming in a void has access to less gas, delivered more slowly, than a galaxy forming at a node. This explains why void galaxies are smaller and less massive. The concept of void mergers is intriguing. Just as galaxies merge when they collide, voids can merge when they expand into each other. Two adjacent voids, growing over time, eventually meet. Their boundaries overlap, and they coalesce into a single larger void. This process is slow, taking billions of years, but it's happening throughout the universe. Simulations show that the largest voids today, the supervoids, are often the result of multiple mergers. The KBC void might have formed this way, starting as several smaller voids that grew and joined together. Void mergers erase small-scale structure, smoothing out irregularities and creating the large, relatively empty regions we observe. They're the opposite of structure formation. Where structure formation builds complexity through gravitational collapse, void mergers build simplicity through expansion and coalescence. Cosmological simulations have become incredibly sophisticated. Modern simulations track billions of particles, representing dark matter, gas, stars, and black holes, evolving them forward through cosmic time using the laws of physics. These simulations reproduce the cosmic web in stunning detail, showing filaments, clusters, and voids that look remarkably like what we observe. But they're not perfect. Simulations depend on approximations, numerical methods that trade accuracy for speed. They also depend on subgrid models, recipes for handling physics that occurs on scales smaller than the simulation can resolve, like star formation or supernova feedback. Different simulations use different recipes, and they produce different results, especially for small galaxies and under-resolved structures. Voids, with their sparse populations and subtle dynamics, are particularly sensitive to these choices. Two simulations with identical initial conditions but different subgrid physics can produce voids with noticeably different properties. This uncertainty affects our ability to interpret observations. When we measure a void's properties and want to compare to theory, which simulation should we use? The answer isn't always clear. There's a philosophical dimension to simulations worth pondering. When we run a simulation of the universe, we're creating a virtual cosmos, a digital twin that evolves according to the same laws as the real universe. In this virtual cosmos, virtual galaxies form, virtual stars ignite, and virtual voids expand. If we could zoom into these simulations with infinite resolution, would we find virtual planets? Virtual life? It's a fun thought experiment, touching on questions about the nature of reality and computation. Some philosophers and physicists take this seriously, arguing that we might live in a simulation ourselves, that what we perceive as reality is actually a computational process running on some substrate we can't access. Voids, in this context, could be computational shortcuts, regions where the simulation doesn't need to calculate as much because there's less going on. It's wild speculation, far beyond anything science can currently test, but it highlights how cosmology intersects with deeper questions about existence and knowledge. Back to observables. One exciting future measurement involves 21-centimeter tomography. Hydrogen, the most abundant element in the universe, emits radio waves at a wavelength of 21 centimeters when its electron flips spin. This emission is extremely weak, but it's ubiquitous, coming from hydrogen throughout the universe. By mapping 21-centimeter emission, we can trace the distribution of neutral hydrogen, including hydrogen in voids that's too diffuse to form stars. Several radio telescope arrays are being built or planned specifically for this purpose. The Square Kilometre Array in Australia and South Africa, Hera in South Africa, and others. These instruments will create three-dimensional maps of hydrogen-spanning cosmic history, showing how voids evolve and how gas flows through the cosmic web. It's going to be revolutionary, opening a window on a component of the universe that's currently almost invisible to us. Another frontier is machine learning. Astronomers are drowning in data. Modern surveys produce terabytes per night, more data than humans can manually analyze. Machine learning algorithms, particularly deep neural networks, are increasingly used to process this flood, identifying galaxies, measuring properties, classifying objects. Applied to void science, machine learning can identify voids automatically in survey data, trace their boundaries, measure their properties, and even predict their evolution. Some researchers are training neural networks on simulations, teaching them to recognize patterns in void structure, then applying those trained networks to real data. The results are promising, often matching or exceeding human performance. Machine learning might also discover patterns we haven't thought to look for, correlations between void properties and other cosmic phenomena that aren't obvious to human intuition. It's a powerful tool, though not without risks. Neural networks are black boxes. They work, but we don't always understand why. If a network finds a pattern, is it real, or is it an artifact of the training data? Validation is crucial. Let me take you to the edge of observability. The cosmic horizon, the farthest distance we can see, is set by the finite age and expansion of the universe. Light from objects beyond the horizon hasn't had time to reach us yet. But the horizon is receding. Every day, objects that were beyond the horizon yesterday cross into visibility. Conversely, objects that are barely within our view today will cross out of view in the future as expansion carries them away faster than light. This creates a strange situation. The universe we can observe is constantly changing, not because the universe itself changes, but because our window on it shifts. Voids near our cosmic horizon are especially interesting. We see them as they were billions of years ago, when they were younger and less empty. By comparing nearby voids to distant ones, we can study void evolution directly, watching how they change over cosmic time. It's like watching time-lapse photography of cosmic structure, except the frames are separated by billions of years and billions of light years. Redshift space distortions provide yet another way to study voids. When we measure a galaxy's redshift, we're measuring how fast it's receding from us, which tells us its distance. But galaxies also have peculiar velocities, their own individual motions in addition to the Hubble flow. These peculiar velocities add to or subtract from the redshift, distorting our distance measurements. In dense regions, galaxies fall toward each other, creating a characteristic squashing of structures along the line of sight in redshift space. In voids, galaxies move outward from the void center, creating an stretching effect. By measuring these distortions, we can infer the velocity field in and around voids, which tells us about the gravitational forces acting on galaxies. This, in turn, constrains dark matter and dark energy. Redshift space distortions are one of the most powerful probes of cosmic structure, and they're especially informative in voids where the dynamics are clean and not confused by complex interactions. The interplay between baryonic physics and dark matter in voids is subtle. Baryonic physics refers to the processes involving normal matter, gas cooling, star formation, supernova explosions, black hole feedback. In dense environments, these processes are vigorous and have dramatic effects on galaxy formation. But in voids, baryonic physics is gentler. There's less star formation, fewer supernovae, less feedback. You might think this makes voids simpler to understand, and in some ways it does. But it also means that small effects, things that would be swamped by more violent processes in dense regions, become important in voids. The precise cooling rate of gas, the efficiency of star formation in low-density environments, the propagation of ionizing radiation through sparse gas, these details matter in voids. And they're hard to model because they depend on microphysics that's difficult to calculate from first principles. This is where observations of void galaxies become invaluable. By studying real galaxies in real voids, we can calibrate our models of baryonic physics and understand how these processes operate in different environments. Cosmic strings, if they exist, would interact interestingly with voids. Cosmic strings are hypothetical one-dimensional defects in spacetime, relics from the early universe when the cosmos underwent symmetry-breaking phase transitions. They'd be incredibly thin, narrower than a proton, but stretched across cosmic distances, and they carry enormous tension, creating strong gravitational effects. As cosmic strings move through space, they'd leave wakes behind them, walls of overdensity where matter was gravitationally pulled toward the string as it passed. These wakes could seed structure formation, creating patterns that don't match what we'd expect from inflation alone. In voids, where structure formation is slow and subtle, cosmic string wakes might be detectable as unusual filaments or sheets of galaxies cutting through otherwise empty regions. Searches for cosmic strings have come up empty so far, suggesting they're either very rare or don't exist. But the search continues, and voids are one of the places researchers are looking. Let's consider the cultural and historical impact of discovering we live in a void. When Copernicus argued that Earth wasn't the center of the solar system, it was revolutionary, challenging centuries of geocentric thinking and undermining religious doctrines about humanity's special place in creation. When Hubble showed that the universe extends far beyond the Milky Way and is expanding, it was another paradigm shift, forcing humanity to confront its cosmic insignificance. The discovery that we live in a void is smaller in comparison, but it's part of the same tradition. Each step showing us that we're less special, less central, less typical than we thought. We're not at the center of the solar system. We're not at the center of the galaxy. We're not at the center of the universe. And now we're not even in an average region. We're in an underdense backwater, a cosmic rural area far from the action. It's humbling. It reinforces the Copernican principle even as it challenges it. And it raises the question, what will the next discovery be? What other assumptions about our place in the cosmos will fall? There's a connection to anthropology worth exploring. Human civilizations throughout history have told stories about their place in the world. Origin myths, cosmologies, religious narratives. These stories often place humanity at the center, either literally or metaphorically. The cosmos revolves around us, or we're the reason the cosmos exists, or we have a special relationship with the divine. Modern cosmology has systematically dismantled these stories, replacing them with a narrative where we're accidental, peripheral, insignificant on cosmic scales. This has been psychologically difficult. It's been linked to existential anxiety, nihilism, the cosmic loneliness that some people feel when contemplating the vastness of space and our smallness within it. Learning that we live in a void might intensify this feeling. We're not just small and insignificant. We're also isolated, sitting in an empty bubble, separated from the main currents of cosmic activity. But there's another way to look at it. Maybe our isolation is what allowed us to develop. Maybe being away from the chaos gave us the time and stability we needed to evolve intelligence, build civilizations, and start asking these questions. Maybe the void is not a prison but a sanctuary. Finally, let's talk about something I haven't touched on, the sound of the void. Not literal sound, because space is a vacuum and sound waves can't propagate. But information can propagate, and information has rhythms and patterns that can be translated into sound. Some astronomers do exactly this, converting astronomical data into audio, a process called sonification. They take measurements like galaxy distributions or cosmic microwave background fluctuations and map them to pitches, volumes, or timbres. When you sonify a void, you hear not much. The sparse distribution of galaxies translates to sparse notes, long silences punctuated by occasional tones. It's eerie, haunting, the audio equivalent of a vast empty space. Contrast this with the sound of a galaxy cluster, which is dense and chaotic, a cacophony of overlapping notes. Sonification isn't just an art project. It can reveal patterns that are hard to see in visual representations, especially patterns in time series data or multidimensional datasets. And it makes astronomy accessible to people who are blind or visually impaired, allowing them to experience the cosmos through sound. The void has its own voice, and its silence broken by whispers, echoes in an empty hall. So where does all this leave us? Living in a void, grappling with what that means for our measurements and our understanding. Developing new tools and techniques to study voids, from gravitational lensing to 21-centimeter tomography to machine learning. Building simulations that recreate cosmic structure in stunning detail, then comparing them to observations to test our theories. And slowly, painstakingly, piecing together a more complete picture of the universe, one that accounts for our location and its effects. The work continues. The questions multiply, but that's the nature of science. Every answer breeds new questions. Every solved mystery reveals deeper mysteries beneath. We're living in a void, yes, but we're also living in the most exciting era of cosmology ever. An era where we have the tools and knowledge to probe the universe's deepest secrets. The void is just one of those secrets, and we're unlocking it one observation at a time. Let me take you into the realm of void connectivity and topology. Voids aren't isolated bubbles floating independently in space. They're interconnected, forming a network, a cosmic sponge where the holes connect to other holes through narrow throats and tunnels. Mathematicians describe this using something called percolation theory, borrowed from studies of how fluids flow through porous materials. In the cosmic context, percolation asks, if you could travel through voids without crossing dense regions, how far could you go? The answer is surprising. Most voids connect to their neighbors, creating pathways that span enormous distances. You could, in principle, travel from one side of the observable universe to the other while staying in underdense regions, hopping from void to void through connecting channels. This has implications for how matter flows through the universe and how isolated void galaxies really are. Even deep in a void's interior, there might be tenuous connections to other voids, thin filaments of slightly higher density that act as bridges. The shapes of voids tell stories about the forces that created them. You might expect voids to be spherical, since spheres are the natural shape for an expanding bubble. But real voids are irregular, elongated, sometimes flattened like pancakes or stretched like cigars. These deviations from sphericity reflect the initial density fluctuations that seeded the voids and the surrounding gravitational influences that shaped their growth. A void that formed between two massive clusters might be compressed in one direction and elongated in another, creating a cigar shape. A void that formed in a region with strong tidal forces from nearby structures might be flattened into a pancake. By measuring void shapes statistically across large samples, cosmologists can constrain the nature of dark energy and test theories of gravity. Different cosmological models predict different distributions of void shapes. Observations to date match the predictions of standard cosmology, but the uncertainties are still significant enough to leave room for alternatives. Now consider the metallicity problem in voids. Metallicity, in astronomy, refers to the abundance of elements heavier than hydrogen and helium. These heavy elements are made in stars through nuclear fusion and scattered into space when stars die. Over cosmic time, successive generations of stars enrich the interstellar medium with metals, gradually increasing the metallicity. In dense regions with lots of stars, this enrichment proceeds quickly. In voids, it proceeds slowly because there are fewer stars. But here's the puzzle. Some void galaxies have metallicities that seem too high for their environments. They contain more heavy elements than we'd expect given their star formation histories and isolation. Where did those metals come from? One possibility is that these galaxies aren't as isolated as they appear. Maybe they formed in denser regions, accumulated metals there, then migrated into the void. Or maybe there's been metal transport, gas enriched by stars in one galaxy being expelled and traveling through the void to enrich another galaxy. This could happen through galactic winds, powerful outflows driven by supernovae that push metal-rich gas out of galaxies at velocities high enough to escape into the intergalactic medium. Galactic winds in voids behave differently than in dense environments. In a cluster, a galaxy's wind runs into the hot intracluster medium, getting shocked and stripped away. In a void, there's no dense medium to stop it. The wind just keeps going, potentially traveling millions of light years before dispersing. This means void galaxies might pollute vast volumes of space with their enriched gas, creating extended halos of metals around themselves. Some of this gas might eventually fall back onto the galaxy, recycled through what's called a galactic fountain. Some might escape entirely, drifting through the void until it encounters another galaxy or filament. Detecting these winds and halos is challenging because the gas is extremely diffuse and doesn't emit much light. Absorption line spectroscopy, looking at how background quasars' light is absorbed by foreground gas, is the primary technique. Recent observations have found hints of extended metal halos around some void galaxies, supporting the idea that winds distribute metals broadly through voids. Let's explore the concept of fossil groups in voids. A fossil group is what remains after a group of galaxies has fully merged into a single massive galaxy. Most of the original group members have spiraled inward and coalesced, leaving behind a solitary giant surrounded by a sparse population of small satellite galaxies. Fossil groups are relatively common in the universe, but they're especially interesting in voids because they represent a different formation pathway. How does a group form in a void where matter is sparse? One possibility is that the group formed outside the void and drifted in, as I mentioned earlier. Another is that the void wasn't always so empty. Perhaps early in cosmic history, this region had enough matter to assemble a group, and only later did expansion drain the surroundings and create the void we see today. Studying fossil groups in voids can tell us about the assembly history of structures and how environmental conditions affect group evolution. There's a class of galaxies called void ellipticals that challenges our understanding of galaxy formation. Elliptical galaxies are usually found in dense environments like galaxy clusters. They're thought to form through major mergers, when two large galaxies collide and their spiral disks are destroyed, leaving behind a smooth ellipsoidal distribution of stars. But if major mergers require dense environments where galaxies encounter each other frequently, how do ellipticals form in voids? Some astronomers argue that void ellipticals must have formed elsewhere and migrated. Others suggest that voids were denser in the past, allowing mergers to occur before the void expanded and isolated the resulting ellipticals. A third possibility is that these aren't true ellipticals, but rather early-type spirals that have stopped forming stars and superficially resemble ellipticals. Distinguishing between these scenarios requires detailed observations of individual galaxies, their kinematics, stellar populations, chemical compositions. It's detective work, trying to reconstruct a galaxy's life story from the clues visible in its present-day properties. The Boötes void deserves special attention. Discovered in 1981 by Robert Kirshner and colleagues, it was one of the first supervoids ever identified and remains one of the most studied. Located about 700 million light-years away in the direction of the constellation Boötes, it spans roughly 330 million light-years. When first discovered, surveys found only 60 galaxies in a region where 2,000 would be expected based on average cosmic density. This emptiness was so extreme that Kirshner described it as a hole in the universe. Later, deeper surveys found more galaxies in the Boötes void, revealing that it's not quite as empty as initially thought, but it remains significantly underdense. The Boötes void has been used as a laboratory for testing theories of structure formation. Its size and degree of underdensity are right at the edge of what standard cosmology predicts should be possible. Some alternative cosmological models predict that voids like Boötes shouldn't exist, making its existence a test that these models fail. Quasar deserts are regions where quasars, the bright cores of actively feeding supermassive black holes, are anomalously rare. Some voids qualify as quasar deserts. This makes sense. Quasars require supermassive black holes, which reside at the centers of massive galaxies, and massive galaxies are rare in voids. But the relationship is more nuanced. Not every void is a quasar desert, and not every quasar desert is a void. Some dense regions also lack quasars, possibly because the black holes there have already consumed their gas supplies and gone dormant. The distribution of quasars across the cosmic web tells us about black hole formation and feeding mechanisms. In voids, the few quasars that do exist are precious objects for study. They're likely recently triggered, fed by some unusual event like a minor merger or a cold gas stream, and they offer insights into how black holes grow in low-density environments. The Lyman alpha forest is a series of absorption lines seen in the spectra of distant quasars. created when intervening hydrogen gas absorbs specific wavelengths of light. Each absorption line corresponds to a cloud of neutral hydrogen along the line of sight. By analyzing the forest, astronomers can map the distribution of hydrogen throughout the universe, including in voids. What they find is that even voids contain diffuse hydrogen, spread thinly through the intergalactic medium. The density is low, tens of atoms per cubic meter rather than the thousands or millions found in dense regions, but it's not zero. This residual gas is a relic from the Big Bang, hydrogen that never condensed into stars or was expelled from galaxies. It's slowly being photoionized by the ultraviolet background radiation that permeates the universe, light from all the quasars and stars combined. In some voids, there are patches where the Lyman alpha forest shows no absorption at all, regions so empty that even this diffuse hydrogen is absent. These ultra-empty regions are called voids within voids, the emptiest places in the cosmos. Let me tell you about tidal dwarf galaxies in voids. When two galaxies collide, tidal forces can pull streams of matter out from both galaxies, creating long tails and bridges of stars and gas. Sometimes, knots of material in these tidal features collapse under their own gravity and form new, small galaxies called tidal dwarfs. These galaxies are interesting because they form through a different mechanism than normal galaxies. They're made from pre-enriched material, gas that's already been processed through stars in the parent galaxies, so they have high metallicities despite being young. Most tidal dwarfs are found in interacting systems in dense environments. But occasionally, a tidal dwarf forms during an interaction in a void. These objects are especially puzzling. What happens to a tidal dwarf when the parent galaxies separate and leave it behind in the middle of nowhere? Does it survive as an independent galaxy, or does it disperse? Observations suggest that many tidal dwarfs are short-lived, surviving only a few 100 million years before tidal forces or stellar feedback tears them apart. But some seem to survive longer, becoming permanent fixtures of the cosmic landscape. Dark matter cores versus cusps is a long-standing problem in galaxy formation, and voids offer a unique testing ground. Simulations of dark matter predict that dark matter halos should have cuspy density profiles, steeply rising toward the center. But observations of dwarf galaxies often show chord profiles, with nearly constant density in the inner regions. This discrepancy has been a thorn in the side of the standard dark matter model for decades. Various solutions have been proposed. Perhaps supernova feedback removes dark matter from galaxy centers, or perhaps dark matter has self-interactions that redistribute it. Testing these ideas requires observing galaxies in different environments to see if the core cusp problem is universal or environment-dependent. Void galaxies are ideal for this. They have less star formation and less violent feedback, so if supernova-driven mechanisms are responsible for creating cores, void galaxies should show cuspier profiles. Preliminary studies suggest that void dwarf galaxies might indeed have profiles closer to the cuspy predictions, supporting feedback-based solutions. But the data is still limited and the measurements are difficult. Stellar streams in voids are ghostly structures, remnants of disrupted dwarf galaxies. When a small galaxy passes too close to a larger one, tidal forces can rip it apart, spreading its stars along its orbital path and creating a stream. These streams are common in and around massive galaxies in all environments. But in voids, where interactions are rare, streams are precious records of past events. Each stream represents a dwarf galaxy that met an untimely end, torn apart by its larger neighbor. By counting streams and measuring their properties, astronomers can infer the merger history of void galaxies and test models of hierarchical structure formation. Do void galaxies have fewer streams than galaxies in dense regions, reflecting their quieter lives? Or do they have surprising numbers of streams, suggesting that even voids were busier in the past? Current surveys are beginning to answer these questions, finding that void galaxies do have streams, though generally fewer and older than their counterparts in dense environments. Population 3 stars, the very first stars in the universe, have never been observed directly. They formed a few hundred million years after the Big Bang from pristine hydrogen and helium, with no heavy elements because heavy elements hadn't been made yet. These stars would have been massive, hot, and short-lived, burning through their fuel quickly and exploding as supernovae. Their explosions enriched the surrounding gas with the first heavy elements, seeding future star formation. Where might we find population 3 stars or their remnants today? One possibility is voids. If there are regions in voids that were never enriched by stellar feedback, pockets of primordial gas that have sat undisturbed for billions of years, then population 3 stars might still be forming there today. It's a long shot, but some astronomers are searching. The James Webb Space Telescope, with its ability to see extremely distant and faint objects, is ideally suited for this hunt. If a population 3 star were forming in a nearby void, Webb might detect its unique spectral signature, devoid of metal absorption lines. Void magnetic fields, which I touched on earlier, have an origin problem. Where do magnetic fields in voids come from? In dense regions, fields are amplified by galaxy dynamics, turbulence, and dynamo processes. But in voids, these mechanisms are weak or absent. One possibility is that the fields are primordial, created in the very early universe through processes like inflation or phase transitions, then stretched and diluted as the universe expanded. Another is that they're generated by more exotic sources like cosmic strings or primordial black holes. A third possibility is that they're not generated in voids at all but leak in from surrounding regions, diffusing slowly through the intergalactic medium. Distinguishing between these scenarios requires measuring void field strengths and structures with high precision, something that's challenging with current technology. But next-generation radio telescopes like the Square Kilometre Array will have the sensitivity to map magnetic fields in voids across vast volumes, potentially solving this mystery. Ultra-diffuse galaxies, or UDGs, are galaxies with very low surface brightness, spread out over large areas so that they're difficult to see. They were discovered relatively recently, in large part because they're so faint that they were overlooked in earlier surveys. UDGs are found in various environments, from clusters to isolated regions, and their formation mechanism is debated. Some might be failed galaxies, objects that started forming in dark matter halos but never accumulated much gas or formed many stars. Others might be puffed-up dwarfs expanded by internal processes like stellar feedback. In voids, UDGs are especially intriguing because they might represent the extreme low-mass end of galaxy formation in underdense environments. If you're trying to form a galaxy in a region with very little matter, you might end up with something diffuse and barely visible, a UDG. Observationally characterizing UDGs in voids is difficult precisely because they're so faint. But efforts are underway, using sensitive wide-field surveys to identify these ghostly objects and study their properties. Let's discuss void velocity fields in more detail. The velocity field is the pattern of how galaxies are moving through space, driven by gravity. In dense regions, galaxies fall toward mass concentrations, creating infall patterns. In voids, galaxies move away from the void center toward the denser walls, creating outflow patterns. Measuring these flows requires precise distance measurements independent of redshift, because redshift conflates distance with velocity. This is hard, but not impossible. By using distance indicators like the Tully-Fisher relation, which relates a galaxy's rotation speed to its intrinsic brightness, astronomers can measure distances and velocities separately. The resulting velocity maps show clear outflow signatures in voids, confirming that voids are indeed expanding. Interestingly, the outflow velocities are typically a few hundred kilometers per second, substantial but not enormous. This tells us about the mass distribution in and around voids. There's enough mass on the void walls to pull galaxies outward, but not enough mass in the void itself to hold them back. The relationship between void size and galaxy properties is a statistical goldmine. Do galaxies in larger voids differ systematically from galaxies in smaller voids? Early studies suggested yes. Galaxies in larger voids tend to be even bluer and more star-forming than those in smaller voids, as if the greater isolation gives them access to more pristine gas. But later studies found this trend is weak or absent once you control for other factors like galaxy mass. The picture is complicated. Larger voids are emptier, yes, but they're also older and have had more time to drain their gas reserves. Smaller voids might be younger, still in the process of forming, and retaining more gas. Disentangling these effects requires careful statistical analysis of large galaxy samples. It's not enough to look at a few individual galaxies. You need hundreds or thousands to see the trends emerge from the noise. Void AGN, active galactic nuclei in voids, are rare but revealing. Most AGN reside in relatively dense environments where gas is available to feed the central supermassive black hole. In voids, gas is scarce, so AGN should be even rarer. But they're not completely absent. When astronomers find an AGN in a void, it's an opportunity to study black hole feeding under extreme conditions. What's triggering the activity? Is it a merger, even a minor one, with a dwarf galaxy? Is it a cold gas stream falling into the galaxy? Or is the black hole consuming leftover gas from earlier epochs, slowly accreting residual material? The AGN luminosity function, the distribution of AGN by brightness, is different in voids than in dense regions. Void AGN tend to be less luminous on average, suggesting that they're fed at lower rates. This matches expectations. Less gas means less fuel, which means weaker activity. Supernova rates in voids are lower than in dense regions, simply because there are fewer stars. But the types of supernovae might differ. Type Ia supernovae, used as standard candles to measure cosmic distances, come from white dwarfs in binary systems. They're found in galaxies of all ages. Type II supernovae come from massive stars and are found primarily in regions of active star formation. In voids, the overall star formation rate is lower, so Type II supernovae should be rarer relative to Type Ia. This difference could introduce a bias if we're using supernovae to measure distances in voids. If void supernovae have slightly different properties on average than supernovae elsewhere, and we're using them to calibrate the cosmic distance ladder, we might be introducing systematic errors. This is one of the concerns raised in the Hubble tension debate. Are void supernovae systematically different, and if so, is that affecting our measurements? So far, detailed studies of individual void supernovae haven't found significant differences, but the samples are small. Void to filament transitions are dynamic regions worth studying in their own right. As a galaxy moves from the void interior toward the wall, the environment changes gradually. Density increases, nearby neighbors become more common, tidal forces strengthen. This environmental gradient affects the galaxy's evolution. Star formation might get triggered as the galaxy encounters denser gas in the filament. Or it might get quenched if interactions strip away the galaxy's gas. Observationally, we can identify galaxies at different positions in this transition and compare their properties, effectively creating a timeline of environmental transformation. What we see is that galaxies entering filaments from voids often show enhanced star formation, a burst of activity as they encounter new gas supplies. But this enhancement is temporary. Further into the filament, galaxies start showing signs of quenching, their star formation shutting down as they get stripped or consumed by larger neighbors. The concept of void probability functions extends to higher-order statistics. I mentioned earlier that void probabilities describe the likelihood of finding a void of a given size. But we can go further, measuring the correlation between voids, the shapes of voids, the alignments of voids with nearby structures. These higher-order statistics contain additional information about cosmology and gravity. For example, if voids tend to be aligned with nearby filaments in a particular way, that tells us about the tidal forces that shape them. If voids of certain sizes cluster together more than expected, that tells us about the initial conditions of structure formation. Extracting these statistics from data requires sophisticated algorithms and massive computing power, but the payoff is worth it. Tighter constraints on dark energy, dark matter, and the fundamental laws of physics. Cosmic variance is an issue that plagues void studies. Because voids are large, you can't fit many of them in a given survey volume. Even the largest surveys to date only contain dozens of supervoids. This means that the statistical sample is small, and small samples have large uncertainties. We might measure the properties of voids in our local universe and find that they're consistent with our models, but that doesn't mean the models are correct. Maybe we just got lucky, and our local region happens to match predictions even though the global universe behaves differently. This is cosmic variance, the fundamental uncertainty that comes from observing only one universe, or rather, only one small piece of one universe. To beat cosmic variance, we need to observe larger volumes, probing farther into the cosmos and capturing more voids in our surveys. Future missions will help, pushing the boundaries of observable volume and improving our statistical power. Void dwarf galaxies are a population unto themselves. These are small galaxies, often containing only a few billion stars, living in the most isolated environments in the universe. They're incredibly faint and difficult to detect, but when we find them, they're treasure troves of information. Dwarf galaxies are thought to be the building blocks of larger galaxies, the small objects that merge and coalesce over cosmic time to form giants like the Milky Way. In dense regions, dwarfs interact frequently, merging or being tidally disrupted. In voids, they survive intact, preserving their primordial properties. By studying void dwarfs, we can learn what the earliest galaxies were like, before mergers and interactions complicated things. Void dwarfs have low metallicities, as expected given their low star formation rates and isolation. They have irregular morphologies, often clumpy and asymmetric, suggesting that they're still actively assembling from gas infall. And they have unusual dark matter contents. Some void dwarfs appear to have very high dark matter fractions, as if they're dark matter halos that barely manage to light up with star formation. The timing of structure formation in voids lags behind denser regions. In the early universe, when matter was still relatively smooth and homogeneous, structure began forming everywhere, but at different rates depending on local density. Dense regions collapsed quickly, forming stars and galaxies within the first billion years after the Big Bang. Voids lagged. Their lower densities mean gravitational collapse proceeded more slowly. Some void galaxies might not have formed until several billion years after the Big Bang, making them cosmologically young even though the universe itself is old. This has observational consequences. If we look at high redshift galaxies, objects seen as they were in the early universe, we're biased towards seeing galaxies in dense regions because that's where structure formed first. Void galaxies at high redshift are even harder to find than nearby ones. This creates a selection effect in our understanding of galaxy formation. We know a lot about how galaxies form in dense environments and relatively little about how they form in underdense ones. Now let's get speculative about the far future. As the universe ages and dark energy continues driving accelerated expansion, voids will grow ever larger and emptier. Galaxies on void walls will be pushed farther apart. Eventually, billions of years from now, some void galaxies will cross their cosmic event horizons, the distance beyond which they can never communicate with each other even in principle. These galaxies will be causally disconnected, unable to ever interact or even know about each other's existence. The universe will fragment into isolated islands, each containing a galaxy or small group, surrounded by an endless void that expands faster than light can cross it. Civilizations in these island galaxies, if any exist, will see a dark sky with no other galaxies visible. They'll have no way to know that a larger universe ever existed. Their astronomy will be limited to their own galaxy and maybe a few nearby satellites. They won't be able to measure the Hubble expansion because there will be nothing to expand away from them that they can see. They won't know about the cosmic microwave background because it will have redshifted into undetectability. They'll be trapped in an observational prison, unable to access the cosmological knowledge we take for granted. This is called the cosmic dark age future, and it's our eventual fate if dark energy remains constant or strengthens. But perhaps dark energy doesn't remain constant. Perhaps it evolves, weakening over time, allowing gravity to halt the runaway expansion. In that scenario, the future would be different. Voids might stop growing. Structure formation might resume, though at a glacial pace. The universe might reach a new equilibrium, a static state where expansion and gravity balance. Or perhaps dark energy eventually reverses sign, becoming attractive rather than repulsive, and the universe begins to recollapse. In that case, voids would shrink, filling in as matter flowed back toward average density. The cosmic web would blur and eventually disappear as everything fell together in a reverse of the Big Bang, a big crunch. Whether any of these alternatives is possible depends on the nature of dark energy, which we don't understand. Observations suggest dark energy is constant, consistent with a cosmological constant, but the uncertainties are large enough that evolution or reversal can't be ruled out. Some researchers have proposed using voids as cosmological standardizable objects, analogous to standard candles but in 3 dimensions. If we could identify a characteristic void size that's constant across the universe, determined by fundamental physics rather than local conditions, we could use voids as rulers to measure cosmic distances and expansion. The idea is that there's a maximum void size set by the Hubble time, the age of the universe. Voids can't grow larger than expansion and gravitational dynamics allow in a given time. By measuring the apparent size of voids at different redshifts, we could track how the expansion rate has changed over cosmic history. It's a clever idea, but implementing it is challenging. Void sizes aren't uniform. They span a wide range, and picking out a characteristic scale from the distribution requires careful analysis. Early attempts have shown promise, with void-based distance measurements broadly agreeing with other methods. But the technique needs refinement before it can compete with supernovae or other established standard candles. Let me introduce you to the Eridanus supervoid, another named void that's garnered attention. This void is about 1 billion light-years across and sits roughly 3 billion light-years away in the direction of the constellation Eridanus. What makes it notable is its association with a feature called the CMB cold spot, an anomalously cold region in the cosmic microwave background. When the cold spot was discovered, it was puzzling because it's colder than statistical fluctuations should allow. One proposed explanation is the integrated Sachs-Wolf effect from the Eridanus supervoid. Photons passing through this enormous underdensity lose more energy than usual, creating the cold spot. However, this explanation is controversial. Calculations suggest that even a supervoid this large shouldn't create a cold spot as pronounced as what's observed. The cold spot might be a statistical fluke, or it might be caused by something else entirely. The debate continues, and the Eridanus supervoid remains a subject of active research. Void catalogs are compilations of identified voids from galaxy surveys, listing their positions, sizes, shapes, and other properties. Several major void catalogs exist, each based on different surveys and using different identification algorithms. These catalogs are publicly available, allowing researchers worldwide to study voids without having to identify them from scratch. But comparing catalogs reveals discrepancies. The same region of space might contain one large void in one catalog and several smaller voids in another, depending on the algorithm used. This isn't necessarily a problem. It reflects the fact that void boundaries are fuzzy and somewhat arbitrary, but it does mean that results can depend on which catalog you use. Standardizing void identification is an ongoing effort, with workshops and working groups dedicated to developing consensus methods. I haven't talked much about the electromagnetic background radiation in voids. Besides the cosmic microwave background, there's also the infrared background, X-ray background, and gamma-ray background, each produced by different source populations. In voids, these backgrounds are slightly dimmer because there are fewer sources. This creates subtle variations in the background radiation across the sky, patterns that correspond to the large-scale structure. By mapping these variations with sufficient precision, we can infer the distribution of matter, including voids, without even directly observing galaxies. It's like seeing the shadows cast by structures rather than the structures themselves. This technique is still being developed, but it holds promise for studying the universe's largest features where galaxy surveys become incomplete. Finally, consider the philosophical question: what is nothing? Voids make us confront this question scientifically. Is a void truly empty, or is it filled with things we can't detect? Dark matter, dark energy, neutrinos, gravitational waves, quantum fields, all of these permeate voids. Even the emptiest void contains the quantum vacuum, seething with virtual particles and zero-point energy. So voids aren't nothing in any absolute sense. They're regions with less of the stuff we can see, but they're still full of the stuff we can't. This connects to deeper questions in physics about what constitutes reality and whether empty space can even exist. Quantum field theory suggests that perfect emptiness is impossible, that the vacuum is an active, dynamic entity. Voids, then, are not absences but different arrangements of presence, places where the visible yields to the invisible, where galaxies step back and the fundamental fields take center stage. We're living in a void, surrounded by cosmic emptiness that stretches for hundreds of millions of light years in all directions. But that emptiness is full of questions, mysteries waiting to be explored. Every observation refines our understanding. Every new survey reveals unexpected details. Every theoretical advance suggests new tests. The void is not a barrier to knowledge. It's an invitation to look deeper, to question harder, to push the boundaries of what we can observe and understand. And as we do, we're not just learning about this particular void or about cosmic structure generally. We're learning about the universe itself, its history, its composition, its ultimate fate. The void is a window, and through it, we're glimpsing the fundamental nature of reality. That's the true gift of living here, in this vast, empty, magnificent corner of the cosmos. The thermal history of voids tells a story rarely discussed. In the first few 100 million years after the Big Bang, before stars formed, the entire universe was cooling uniformly. Hydrogen gas everywhere had roughly the same temperature, dropping as space expanded. Then the first stars ignited and everything changed. These stars emitted intense ultraviolet radiation that heated and ionized the surrounding gas. In dense regions where stars formed abundantly, this reionization heating was vigorous and thorough. In voids, reionization proceeded differently. The ultraviolet photons had to travel farther between sources, taking longer to heat the sparse gas. Some void regions might have remained cool and neutral for hundreds of millions of years after their denser neighbors were fully ionized. This delay would affect subsequent structure formation. Cool gas collapses more easily than hot gas, so these late reionizing void regions might have experienced a brief window of enhanced star formation before the radiation finally caught up and heated them too. Evidence for this scenario comes from studying the thermal state of the intergalactic medium at different cosmic epochs through absorption line systems. Void substructure is more complex than simple models suggest. When you simulate a void at high resolution, you find that it's not uniformly underdense. There are variations within variations, a hierarchy of smaller underdense regions separated by thin filaments where a few galaxies huddle. These internal filaments are incredibly tenuous, containing perhaps 1/10 the galaxy density of typical filaments outside voids, but they're still denser than the deepest void interiors. Galaxies forming along these internal filaments have access to slightly more matter than those in the deepest voids, which affects their properties. This creates a spectrum of void galaxy types, from extremely isolated objects in void cores to slightly less isolated objects along internal filaments. Observationally distinguishing these populations requires three-dimensional mapping at high resolution, something only the latest surveys can provide. The spin alignment of void galaxies presents an unexpected pattern. Galaxies spin, rotating around their axes as they orbit through space. The direction of the spin, encoded in what's called the angular momentum vector, isn't random. Galaxies tend to align their spins with the large-scale structure around them, an effect called intrinsic alignment. In filaments, galaxies preferentially spin with their angular momentum parallel to the filament axis. In sheets, they align perpendicular to the sheet. What about voids? Studies suggest that void galaxies show weaker alignments than galaxies in denser environments, as if the isolation has allowed them to retain their primordial spin orientations without being torqued by tidal forces from neighbors. This is interesting because it means void galaxies might preserve information about the initial angular momentum field of the universe before interactions scrambled everything. Gravitational potential wells in voids are shallow compared to those in dense regions, but they still exist. Every galaxy sits at the center of a dark matter halo, which creates a gravitational well. In voids, these wells are isolated, like valleys separated by high plateaus. Matter falling into one well has little chance of reaching another. This creates what physicists call a potential landscape, a topographical map of gravitational highs and lows. The landscape in voids is gentle and smooth, while the landscape in clusters is steep and rugged. This difference affects everything from galaxy formation to the propagation of gravitational waves. A gravitational wave passing through a void experiences less gravitational lensing than one passing through a cluster, making void regions valuable for gravitational wave astronomy precisely because they introduce minimal distortion. Baryon acoustic oscillations leave their imprint even in voids. These oscillations are sound waves that propagated through the early universe's plasma, before electrons and protons combined to form neutral atoms. The waves traveled a specific distance, determined by the sound speed and the age of the universe at recombination, creating a characteristic scale in the matter distribution. This scale, about 500 million light-years today due to expansion, appears as a preferred separation between galaxies. It's a subtle effect, only visible statistically across large volumes, but it's one of cosmology's most powerful tools for measuring dark energy and the universe's geometry. In voids, the baryon acoustic oscillation signal is present but distorted. The underdensity modifies the clustering pattern, shifting the characteristic scale slightly. By measuring this shift and comparing it to predictions, cosmologists can test whether gravity behaves as expected in underdense regions or whether modifications are needed. The escape velocity from voids is a concept worth contemplating. If you're a galaxy sitting in a void, how fast would you need to move to escape the void's gravitational influence? The answer depends on the void's mass profile and surrounding structures. For typical voids, escape velocities are a few hundred kilometers per second, comparable to the peculiar velocities galaxies actually have. This means that some galaxies can and do escape voids, drifting outward toward the walls over cosmic time. But most don't. They're trapped, not by strong gravity holding them in, but by weak gravity failing to pull them out. It's a subtle distinction, but an important one. Voids don't actively confine galaxies. They just fail to provide the gravitational gradients needed to move galaxies elsewhere. Void tracers are objects or phenomena that mark the presence of voids without requiring complete galaxy surveys. One example is the Lyman alpha forest I mentioned, which traces hydrogen distribution. Another is the kinetic Sunyaev-Zeldovich effect, where hot gas moving relative to us scatters cosmic microwave background photons and creates temperature distortions. In voids, the gas is sparse and cool, so this effect is weak but still detectable with sufficiently sensitive instruments. A third tracer is weak gravitational lensing of background galaxies. By measuring how light from distant galaxies is very slightly deflected by foreground matter, including the matter deficit in voids, we can map void locations and properties. These alternative tracers complement galaxy surveys and provide independent checks on void properties. The isotropy of voids, whether they're the same in all directions, is an important test of the cosmological principle. If voids in one part of the sky differ systematically from voids elsewhere, it would suggest large-scale anisotropy in the universe, a violation of our fundamental assumptions. Searches for such anisotropies have been conducted using void catalogs, comparing void properties in different sky regions. So far, no significant anisotropies have been found. Voids appear statistically similar everywhere, supporting the idea that the universe is indeed isotropic on large scales. But these tests are limited by sample size and observational systematics. More sensitive searches with larger datasets might yet reveal subtle violations. Void merging rates can be estimated from simulations, providing another constraint on cosmology. If we know how quickly voids merge, we can work backward to infer the initial density fluctuations that seeded them and the expansion history that governed their growth. Simulations show that void mergers become less frequent as the universe ages and dark energy dominates. In the early universe, when matter dominated, voids grew and merged vigorously. Today, with dark energy driving accelerated expansion, void merger rates have slowed. This evolution is encoded in the size distribution of voids at different redshifts. By measuring void populations at different cosmic epochs and tracking how the distribution changes, we can test dark energy models. Primordial black holes, if they exist, would be distributed differently in voids versus dense regions. These hypothetical objects, formed in the very early universe from density fluctuations, would serve as dark matter or a component thereof. Unlike particle dark matter, which clusters gravitationally like normal matter, primordial black holes would have formed from rare, high-density peaks in the primordial fluctuation field. Their distribution might not follow the cosmic web at all, or it might follow it with different biases than galaxy distributions. In voids, primordial black holes could be the dominant form of dark matter, outnumbering the sparse galaxies and providing most of the gravitational mass. Detecting them is challenging because black holes don't emit light, but they do cause gravitational lensing. Searches for lensing events caused by compact objects in voids might reveal primordial black holes if they're abundant. The acoustic horizon at recombination sets a fundamental scale in cosmology. The maximum distance sound waves could have traveled before the universe became transparent. This scale is imprinted on the distribution of matter and appears in the sizes of the largest structures. Voids larger than the acoustic horizon shouldn't exist in standard cosmology because there wasn't enough time for underdensities that large to form. Yet some observed voids approach or possibly exceed this limit, creating tension similar to the Hubble tension but for structure formation. Are these voids really as large as they appear, or are measurement uncertainties making them seem bigger? Are they statistical flukes, rare outliers that we happen to observe? Or do they indicate that our models of structure formation need revision? This question remains open. Void galaxies as gravitational wave sources is a futuristic but intriguing idea. When binary black holes or neutron stars merge, they emit gravitational waves detectable by LIGO and similar instruments. Most detected mergers have been from dense regions where stars are abundant and binary systems common. But void galaxies also contain black holes and neutron stars, and occasionally these objects merge. The rate is much lower, but it's not zero. A merger in a void would produce a gravitational wave signal that's effectively clean, having passed through a simple gravitational environment without significant lensing or distortion. By comparing signals from void mergers to those from cluster mergers, astronomers could study how environment affects binary evolution and merger rates. The role of voids in cosmic ray propagation extends beyond what I mentioned earlier. Cosmic rays are charged particles, which means they're deflected by magnetic fields. In dense regions with strong fields, cosmic rays scatter chaotically, following tangled paths that bear little resemblance to straight lines. Their trajectories become diffusive, like drunk walks through space. In voids with weak magnetic fields, cosmic rays travel more ballistically, following straighter paths. This means that ultra-high-energy cosmic rays detected on Earth might have originated from sources in voids, traversing the underdense regions without significant deflection. Mapping cosmic ray arrival directions and correlating them with void positions could reveal void sources we haven't detected through electromagnetic radiation. The chemical evolution in void galaxies proceeds at a glacial pace compared to galaxies in rich environments. Each generation of stars produces heavy elements and returns some fraction to the interstellar medium through stellar winds and supernovae. These elements mix with pristine gas and are incorporated into the next generation of stars. The timescale for this enrichment depends on the star formation rate. In void galaxies with low star formation, enrichment takes longer. Some void dwarf galaxies might have metallicities comparable to galaxies in the early universe, billions of years ago, because they've been slowly forming stars at a trickle. These galaxies are effectively frozen in time, their chemical evolution stalled by lack of material. Void filling factor is the fraction of the universe's volume occupied by voids. Different definitions of what constitutes a void give different answers, but roughly 40 to 60% of the universe's volume is in voids, depending on the density threshold used. This means that most of the universe by volume is underdense. Yet most of the mass is not in voids. It's concentrated in filaments and clusters. This asymmetry between volume and mass is fundamental to understanding cosmic structure. The universe is mostly empty space with matter clustered in relatively small volumes. Voids dominate spatially, but they're insignificant gravitationally. Cross-correlations between voids and other cosmic phenomena reveal hidden connections. For example, correlating void positions with gamma-ray background maps shows that voids emit fewer gamma rays, as expected since they contain fewer galaxies and thus fewer gamma-ray sources. Correlating voids with the distribution of fast radio bursts might reveal whether these mysterious events are more or less common in underdense regions. Correlating voids with large-scale peculiar velocity fields shows how matter flows out of voids and into surrounding structures. Each correlation is a test of our models and a potential source of new insights. The entropy of void gas is lower than that of cluster gas, reflecting its thermal history. Entropy, in the thermodynamic sense, measures the disorder or randomness of a system. Gas that's been heated and stirred by supernovae, black hole feedback, and galaxy mergers has high entropy. Pristine gas that's been gently cooling as the universe expands has low entropy. Void gas falls into the latter category. It hasn't experienced much heating, so it retains a memory of its initial state. This low-entropy gas is easier to cool and condense, which paradoxically makes it better fuel for star formation if it can be collected. But in voids, the collection process is slow because gravity is weak. Observational biases in void studies are numerous and pernicious. Voids are defined by the absence of galaxies, but our galaxy surveys are incomplete. We miss faint galaxies, distant galaxies, and galaxies obscured by dust or located behind bright foreground objects. This incompleteness means that some voids in our catalogs might not be voids at all. They might just be regions where we failed to detect the galaxies that are actually there. The bias is worse for distant voids because our surveys become shallower with distance. Correcting for these biases requires careful modeling of survey selection functions and often involves simulating mock surveys to understand what we might be missing. The void luminosity function describes the distribution of galaxy brightnesses in voids. It differs from the global luminosity function, which averages over all environments. Void galaxies tend to be fainter, with fewer bright galaxies and an overabundance of faint ones. This reflects the slower assembly of mass in underdense regions. Bright galaxies require either lots of mergers to build up mass or very efficient star formation to convert gas into stars. Both processes are suppressed in voids. By measuring the void luminosity function precisely and comparing it to predictions from galaxy formation models, we can test our understanding of how environment influences galaxy growth. Void-finding algorithms come in several flavors, each with strengths and weaknesses. Geometric algorithms identify voids by looking for spherical or ellipsoidal regions devoid of galaxies. Watershed algorithms treat the density field like a topographic map and identify voids as basins between peaks. Tunneling algorithms trace paths through underdense regions, finding interconnected networks of voids. Friends of friends algorithms link galaxies into groups and define voids as the spaces between groups. Each method produces somewhat different catalogs, and there's no consensus on which is best. The choice depends on what scientific question you're asking and what aspects of void structure you care about. Cosmic web connectivity graphs are mathematical representations of how filaments, walls, and voids connect to each other. You can represent the cosmic web as a network, with nodes representing clusters and edges representing filaments, then analyze this network using tools from graph theory. What you find is that the cosmic web has small world properties. Despite being vast, most clusters are connected to most others through relatively short chains of filaments. Voids fit into this picture as the empty spaces between network elements, the gaps in the graph. Analyzing web connectivity helps us understand how matter and information flow through the universe. The impact parameter for photons passing through voids affects their journey in subtle ways. Impact parameter is the closest approach distance between a photon's straight-line trajectory and some object or region. For a photon grazing the edge of a void, the impact parameter is small and gravitational effects are maximized. For a photon passing far from any void, the impact parameter is large and effects are minimal. By studying how cosmic microwave background photons or light from distant quasars is affected as a function of impact parameter relative to known voids, we can probe the mass profiles of voids and test whether they match theoretical expectations. The void filament interface is where most of the action happens in terms of galaxy evolution. Galaxies that form deep in voids stay pristine and isolated, evolving slowly. Galaxies that form in filaments experience frequent interactions, mergers, and environmental effects. But galaxies at the interface experience a mix. Some isolation early in their lives, followed by gradual immersion in denser environments as the void wall pushes them outward. These galaxies show mixed properties, hints of both quiescent void evolution and active filament evolution. They're valuable for understanding environmental transformation, the process by which galaxies change when their surroundings change. Void occupation statistics describe how many galaxies of different types occupy voids of different sizes. Large voids might contain a few dozen galaxies, mostly dwarfs. Small voids might contain only one or two. The relationship between void size and galaxy count is not linear. It depends on complex physics of galaxy formation and on the density threshold used to define the void. By measuring occupation statistics and comparing to models, we constrain how efficiently galaxies form as a function of environment. Thermal pressure support in void gas is negligible compared to dense regions. Gas pressure, from random thermal motions of atoms, can resist gravitational collapse and prevent structure from forming. In clusters, pressure is high enough to significantly affect dynamics. In voids, pressure is so low that it's irrelevant. Gravity and cosmic expansion dominate. This simplifies the physics, making voids theoretically cleaner to model than clusters. Redshift space compression and expansion around voids create distinctive patterns called the Kaiser effect, named after Nick Kaiser, who first described it. In redshift space, which is how we observe the universe since we measure redshifts, not true distances, structures appear distorted by peculiar velocities. Voids appear compressed along the line of sight because galaxies on the near and far sides are flowing outward in opposite directions, reducing the apparent void size. Measuring this compression allows us to infer the growth rate of structure, a key cosmological observable. The lifetime of void galaxies depends on their fate. Some will eventually drift to void walls and merge into larger structures, their identities erased. Others will remain in the void interior for the rest of cosmic time, slowly exhausting their gas supplies and fading into darkness. A third category might be ejected from the void entirely if they acquire large enough peculiar velocities through gravitational interactions. Simulations show that most void galaxies fall into the second category. Eternal isolation, gradually dying as they run out of fuel. Void walls as sites of enhanced structure formation deserve more attention than they've received. The walls are where matter accumulates after draining from voids. This creates local overdensities, regions where the galaxy density is higher than the cosmic average even though the surrounding volume, including the void, is underdense. These walls are where you find some of the universe's largest structures. Superclusters, great walls of galaxies spanning hundreds of millions of light years. The Sloan Great Wall, one of the largest known structures, forms the wall between several voids. Understanding walls is inseparable from understanding voids. They're two sides of the same coin. Empty voids at high redshift offer a time machine to study void evolution. By observing voids in the distant universe, we see them as they were billions of years ago. Comparing young voids to old voids reveals how they evolve, how their galaxy populations change, how their sizes grow. This is harder than it sounds because identifying voids at high redshift requires deep, wide-field surveys that capture enough volume to contain multiple voids. Current surveys are just reaching the depth needed for this work, and the next generation will transform it. Void density contrasts quantify how underdense voids are. The density contrast is defined as the ratio of void density to mean cosmic density, -1. A contrast of -0.9 means the void has 10% of the mean density. -0.95 means 5%. The deepest void interiors have contrasts approaching -0.95, nearly empty by cosmic standards. Measuring density contrasts requires counting galaxies and correcting for observational incompleteness, a challenging task but essential for characterizing voids. The age-velocity dispersion relation in void galaxies differs from that in dense regions. Velocity dispersion measures the random motions of stars within a galaxy. Higher dispersion means older stellar populations in general because star formation creates young, kinematically cold populations while older stars have been dynamically heated. In voids, this relation is shifted, with void galaxies showing lower dispersions for a given age, consistent with quieter dynamical histories. Void expansion rates can be measured directly by tracking galaxy motions over time. This requires observations separated by years or decades, long enough for peculiar velocities to move galaxies appreciable distances. Such measurements are at the edge of current capabilities but will become routine with future astrometric missions like the Space Telescope Gaia's successors. Environmental quenching mechanisms that shut down star formation in dense regions are largely absent in voids. There's no ram pressure stripping because there's no dense intracluster medium to strip gas away. There are no harassment or strangulation effects from repeated close encounters because encounters are rare. Void galaxies shut down star formation primarily by exhausting their gas supplies through slow internal processes, not through environmental effects. Now, after this deep journey into the emptiness, after exploring every facet of voids from their magnetic fields to their quantum substrates, from their galaxy populations to their cosmological implications, we need to step back and ask, what does it all mean? The answer: we are living inside a cosmic void, an underdense bubble in the universe nearly 1 billion light-years across. This is not speculation, it's observation. And yes, there's a problem. Our location might be distorting our measurements of the universe's expansion rate, creating the tension between local and cosmic measurements of the Hubble constant. But whether or not the void fully explains this tension, its existence tells us something profound. It tells us that our place in the cosmos is unusual, that we've been measuring the universe from a perspective that isn't representative of the average. Every number we've calculated, every model we've built, every prediction we've made about cosmic fate has been filtered through the lens of our location. And that location is emptier than most. But here's the remarkable thing: we figured this out. We mapped our neighborhood on scales so vast that light takes hundreds of millions of years to cross them. We compared our local universe to the global picture painted by the cosmic microwave background. We ran simulations containing billions of particles evolving over cosmic time. We built instruments sensitive enough to detect the subtle signatures of voids in gravitational lensing, in cosmic flows, in the distribution of gas between galaxies. We took our isolation and turned it into insight. The void is not a prison. It's a laboratory. It's a natural experiment in what happens when galaxies form and evolve in low-density environments, free from the complications of clusters and filaments. It's a testing ground for general relativity in its weakest regime. It's a window on the cosmic web structure, revealing through its absence what presence creates everywhere else. And most importantly, the void is a reminder that the universe doesn't revolve around us, that our perspective is one of countless possible perspectives, that what we see depends on where we stand. This has been the lesson of modern cosmology from the beginning. We are not central, not special, not privileged. We are one planet among billions, orbiting one star among billions, in one galaxy among billions, sitting in a void among thousands. Yet we are the ones asking the questions. We are the ones building the telescopes, running the simulations, analyzing the data. We are the universe's way of understanding itself, and we're doing it from the middle of nowhere, from a bubble of cosmic emptiness, using tools made of atoms forged in ancient stars, guided by mathematics discovered by pattern-seeking minds, driven by curiosity that evolution never intended but somehow produced. The void problem isn't that we're in a void. The problem is that it took us so long to realize it, and now we have to recalibrate. We have to re-examine our measurements, refine our models, account for local structure in our global conclusions. It's work. It's difficult work. But it's also exactly the kind of challenge that drives science forward. Because here's what we're really doing. We're taking a universe 13.8 billion years old and 90 billion light years across, a universe containing structures we can barely imagine and ruled by physics we're still deciphering, and we're making sense of it. We're finding order in chaos, patterns in noise, meaning in emptiness. We're living in a void and using that void to understand everything beyond it. That's not a problem. That's the human story, written on the largest canvas imaginable. We exist in the gaps, in the quiet places, in the cosmic countryside far from the metropolitan centers of galactic activity. And from our isolated outpost, we're mapping the entire cosmos, measuring its age, tracking its expansion, predicting its fate. The void is huge. The universe is huger. And we, impossibly small, implausibly improbable, are here in the emptiness, looking outward, asking questions, finding answers. The void doesn't diminish us. It frames us. It shows us who we are. Explorers of the infinite, thinkers in the darkness, conscious matter contemplating the void that contains it. And that, in the end, is the most astonishing thing of all. Not that we're in a void, but that we know it. Not that space is mostly empty, but that we filled it with meaning anyway. Not that we're isolated, but that we reached across the isolation and touched the stars. We are living inside a huge void, but the void is living inside an even huger universe. And that universe, through us, has opened its eyes and seen itself. From the emptiest places, the deepest insights emerge. From the void, understanding. From isolation, connection. From a cosmic accident on a pale blue dot in the middle of nowhere, consciousness, curiosity, and the drive to know. That's the problem with the void. And that's why it's not a problem at all. It's an opportunity. It's a gift. It's home. And we're just beginning to understand it.